All right, folks, I just started the recording, so we'll get started here so that we don't take all day. First off, my name is Dylan Perkins. I work at the Advanced Research Computing Center here on campus. If some of you know me, if you don't, hello. Um, it's fun. So today is a little bit weird. Uh, we did, I'll go over this in a little bit, but this workshop is not necessarily being taught by me. It's being taught by our collaborators at CU and CSU. But they were so gracious to come up and help us out with some more advanced topics than we usually get to teach. Um, so today, our learning goals are to know what containers are and what the difference between different container software, how to use containers on Teton, how to do basic parallelization in R, and how to use RMPI. Those are our 4 learning goals. Our agenda, I'll go over the background and how this came about, some logistics here on what we can do, some schedule with our breaks. We'll establish some ground rules for the workshop, and then do a brief little introduction thing, but not too long with that one. So first off, once a month, we have conference calls with the Rocky Mountain Advanced Computing Consortium, in which UW is a member. And at one of these calls, the Thomas Hauser at CU was saying, hey, we got an NSF grant to do some outreach to some under-resourced institutions in the region. So if anybody needs compute or storage, let us know. And I was sitting there thinking, well, we have plenty of compute and storage at UW, but what we don't have is the amount of people to teach workshops. So I responded, and we came up with, all right, let's do some containers training, and then what else? And after thinking about it, it was like, well, most of our R users on Teton run things in serial, so let's see if we can do a parallel R course. And that's kind of what we came up with, and that's how this happened. Also, this is getting recorded. I have all these slides, so maybe you can teach more container stuff later on, but I need to learn how to do it myself. All right, workshop logistics. If you're here physically in the room, the restrooms are on the south side of this building. We're all adults. Get up and leave whenever you need to. Don't ask for permission. Refreshments, we have water fountains over there by the restrooms, and there's vending machines and stuff if you need. If not, there's coffee and hot water for tea over here in the corner, and go help yourself. So at lunchtime here, we do not have lunch provided for everyone, but there are plenty of restaurants nearby, especially across the street on Grand Avenue. Domino's, Sushi, Subway, O'Dwyer's, and obviously the Union has plenty of food shops too. Welcome to eating here if you brought your own too. Zoom folks, the meeting info is here. Feel free to forward along to anyone that you wish. But please mute yourselves. All of your questions will be addressed during the breaks. And since the examples are going to be run on UW's HPC system, Teton, if you don't have a Teton account, you can't follow along with the examples. For you in the room, we have some training accounts, but since we have to have 2-factor login, I have all of those with me right here in this bag. You can, if you're remotely, use your own account on Teton, but please be mindful of your colleagues. If you're taking up a bunch of room on their project space or your home directory, that's why we have these training accounts available so that we can break anything we want. We have an approximate schedule here. It is 9, and so we'll get started with section 1, containerization with Andy. Andy's right over here if he wants to raise his hand. We'll take a break. We'll answer questions from section 1 just before we get started with section 2 with containers on building your own containers on Teton. We'll have lunch, like I mentioned, answers to section 2, basic parallelization in R with Tim Kaiser over here from CSU, and we'll have another break around 2 o'clock. Like I said, this is approximate, so we'll see how far we get to where we need to go. We'll have our answers from question 3, some from section 3, and then using RMPI. At 3 o'clock or roughly, we'll have a Q&A about the overall session if you guys would like to participate in that. So we have some ground rules for this workshop. First off, assume good intentions. If somebody says something that you may not understand, they're not trying to insult you, or trying to help everybody else. This is rule about oops versus ouch. If I perhaps say something that unintentionally hurt somebody's feelings, that's an oops on me, but you guys need to tell me ouch, that hurt me. Please silence your phones if you're here. It'd be really great to not have to hear somebody's weird ringtone. One different thing that I'm trying out is having questions consolidated in one Google Doc, and I'm gonna put this in the Zoom chat here in a little bit so that you all can go do it. No, I didn't do that. I just made this yesterday. Sorry. And so the reason for this is that we get repeat questions sometimes, and some people like further follow-up. So the Google Doc looks like this. First off, the first question is, why did you enroll in this course? I have an example here. I wrote my name, a dash, and then the answer. For questions for ARC, like Teton or how to whatever, write your name, how do I get an account, and then a follow-up from somebody else with a tab indented there. That'd be really great, so that we know that these are related questions. And obviously questions for Andy here and for Tim here. Cool, I will go back to that. And what else would you guys like to have for rules? Any technology rules? Cool, all right. One last thing. So how many of you folks in the room or on Zoom, this is where I will pay attention to chat this time, are UW students? Cool. About half the room. Non-UW students. Nobody much in the room here, but I bet you there's some on chat. Anyway, researchers or professors from UW. Sweet, a couple of you. And there might be some more on Zoom. So we have a good mix of folks here, mostly students, but that's great. We'll get them hopefully working, doing their research better. So with that, I'm going to stop talking and hand it off to Andy to get started with section 1.
All right. Thanks for coming, everyone. I know it's Friday and containers may not be the foremost. See if we can zoom in on this here. Foremost topic on your mind. If we can make these a little bigger. My name is Andy Monahan. I'm at the University of Colorado. So we have a high performance computing center there that we share the main HPC resource with Colorado State University. And my colleague, Tim Kaiser, who will be teaching this afternoon, is from Colorado State. As Dylan mentioned, we are part of the Rocky Mountain Advanced Computing Consortium, which is a number of institutions throughout the Mountain West who share knowledge and resources. So we're presenting today as part of that consortium. And I just want to thank Dylan for organizing this. This is really well organized, so appreciate it. It's great to be able to just come here and have everything set up. If you want to go to this GitHub link, and you can probably Google Research Computing GitHub, or you can just type this in. I set up a repository for this particular course.
First thing before that, you're here and you're logged into the Teams as your log out and log in as the training account. The training account username are right here on the corner of every monitor, and the password is up top there, Wyoming1. That's just because once you go to GitHub, we'll have our other software that we need to use later today, so you don't have to change that. Okay, continue.
Okay. Not sure how to open the. I was going to try to paste this link into the chat here, but okay. For those of you who are on Zoom, Dylan will paste the GitHub link into chat. All right. So outline for this morning is I'll give an introduction of containers, and then talk about a specific containerization software that we use on high performance computers called Singularity, and some of the basic commands for running that. And then we'll dig right into a hands-on exercise on Teton. And then I wanted to talk a little bit about some more advanced topics using containers for MPI, which would be parallel applications that go across nodes on Teton or other HPC resources that you may be using, as well as running containers on GPU nodes. We'll actually run an example with MPI, but GPUs we don't have time today to do. So I'll try to just let you know, those are still some areas where there is a little bit of nuance for running containers. Then we'll have a break, and then after that, we'll dig into building containers. So first half, we're just going to get right in and run containers, and second half, we'll actually go through some of the basics of building your own container. So introduction, what is a container? I think you could probably define it in many ways, depending on who you are. In my view, from a very simple perspective, a container is a portable environment that packages an operating system, software, libraries. You can put compilers in it, data, and workflows. And really, one of the key advantages of containers are the mobility of compute. This is, I think, particularly useful in an academic environment where a lot of the software that you might be using may not be commercially available software, but instead it may be research software that you developed or some colleagues developed, and it's not developed by a team with 20 people on it, and so it may not compile well across different systems. So you can, what a container essentially does is allows you to install that software in its preferred environment. So some flavor, its preferred Linux environment. So some flavor of Linux, whether it be Ubuntu or CentOS or Debian or whatever you want. And you can install specific versions of compilers and libraries and everything else. So you can get that environment that software runs in exactly the way you want it. And that can sometimes be hard if you're trying to compile that same software just in situ on Teton. You may not have the libraries that you need available to compile that. So really, it's kind of putting that in its favorite environment, and then you can move that container is essentially just a file, a big file, and you can move it around to different systems that have containerization software on them, and run them. So what we're seeing now is that containers are starting to be used. For example, if you publish a paper and you have some software that you used to publish that paper, you can actually publish that container as part of the data that would support that paper, so that others would be able to use, if they wanted to use that software or try to reproduce something in your work, they'd have easy access to it, and you wouldn't have to deal with kind of all the email back and forth of helping that person. So there's reproducibility from that perspective, and then just allows you freedom to kind of move around. So if you're we also have instances where users are using our HPC resource and maybe someone else's. So they may be working on 2 or 3 different systems. So containers can really help to streamline that process where you can use the same container to run your workflow on different systems. Any questions on that from anyone? In a reproducible fashion? I would say the ones that we get a lot of interest from, and the ones who are kind of moving towards using it for publications are bioinformatics users in particular. And Tim deals with a lot of bioinformatics users at CSU, I believe. The reason for that is that they typically, so these are folks who are looking through genome sequences and that type of thing, and those tend to be pipelines with maybe 10 pieces of software in them, and they those pieces of software are managed by different institutions. The versions are constantly changing, so they have a lot of challenges with maintaining the kind of a static pipeline in time. And so there's a lot of interest from that community in terms of if I publish some paper on something I found about inherited traits, for example, based on a genome sequencing, and I want that I know that someone might try to reproduce that, then publishing that exact software pipeline in a container is a really good way to at least to make sure that they have the exact software workflow that you used. So the question for those online was, how easy is it to integrate those different pieces of software if they're distributed? You can put them all in the same container in that instance if you want. So you can have more than one piece of software in a container. I should say that. However, you can also coordinate containers through, there's container coordination software. A popular one is called Kubernetes that coordinates Docker containers. So there are ways to also set up workflows that have multiple containers each running a unique piece of software. But you can also, if you have a fairly straightforward workflow and all of the pieces of software in it work pretty well together in the same environment, then you could install all of those pieces of software in the same container. So it's a matter of preference in that instance. So thanks for asking that. Good question. We have another question. We had a question about commercial software development. So can you use containers to run or develop commercial software? As long as, so I, okay, you may have some, it sounds like you have some experience with this. I think I'm probably not the best person to ask on that. I can say from kind of a user, if you can, I think you have to be careful about licensing issues from in terms of moving containers around. So if you can have a container pinging an external license server, then that's generally would be kind of a legal way to do it, because someone couldn't just run the container with a licensed piece of software in it. They'd actually have to have a license that's being served up, or a license file on their system that's being fed into the container through an environment variable. But actually putting a license file in a container would probably be a violation of license terms in most instances. So does that answer your question in general? So there are ways to do it, but you have to kind of be careful that you're not violating terms and Uh, for those of you online who I'm not sure if folks can hear or not, they can. Okay, then I won't repeat that. Um, another the folks online. There was just another comment from a user noting that commercial stuff is kind of case by case. I should mention, since I know a number of you are engineering oriented, MATLAB has, you can use MATLAB's runtime libraries. Have any of you used those? So you can, so MATLAB obviously is a licensed software, but if you want to containerize a piece of your software that you developed in MATLAB, you can containerize, you can create an executable from your MATLAB script. So you essentially compile it into an executable, and then you can install it into a container with MATLAB's runtime libraries, and you can distribute that. What that essentially allows, it makes it immutable from that perspective. So MATLAB's okay with that because it's just an executable, and they're not giving away intellectual property or anything. They're just giving an environment where an unchangeable executable can be run. So we do. I recently built a container for a user who is a MATLAB user where we did that. A little bit on just difference between a virtual machine and a container. Uh, so virtual machines use hardware virtualization. So you'd have a virtual machine is a much bigger image where you might have multiple virtual machines running on a given system. So for example, I think Dylan mentioned earlier that they had a Linux virtual machines running on these, but it took up so much space that the hard drives were filling up, so they removed them from these. So now you just have a Windows operating system, but you can do hardware level OS. That's how, if for those of you who use the cloud, you're generally setting up virtual machines on the cloud. They're more flexible in terms of how you set up security and other things. So it's essentially like setting up your own machine within a machine. The problems with them is that they're not portable, and they're big. So OS, or operating system level virtualization, which is used by containers, you can run multiple containers on, for example, the machine that you're on today, and they can all exploit the host operating system and the resources on that system in the same manner. So they can share libraries, binaries, the OS, the resources underneath. And so they tend to be much more lightweight. They're just a single file, and you can transfer this file just like you would any other file. You can use some sort of file transfer service, SFTP, SCP, Globus, whatever you use to move them around. So they're much more lightweight. They're easy to build. They're easy to update, and there are tens of thousands, if not millions of them at this point that are already available. And I'm going to go over that because that's an important aspect. Chances are, if you're using an application that's fairly common, someone's already built a container for it. And so you can literally be up and running in minutes with that. And I'll go over that. So in terms of containerization software, Docker is by far the largest and most common. It's used in enterprise pretty much exclusively these days. They have a hub that's kind of a publicly available repository of containers called Docker Hub. We're going to pull some containers from Docker Hub today. The only reason we don't use Docker is because of the way that it handles the user privileges at runtime. It essentially requires administrative privileges by users of the container. And so when you're working on shared systems like high performance computing resources, Teton, others, Docker is just, it's not possible to use that as a non-root user on a shared system. And so Singularity is the software we're going to focus on today. It arose as to kind of fill that need. It was developed, I think, at Lawrence Berkeley and Stanford in order to um, researchers were wanting to run Docker containers and couldn't. And so it handles the user space a little bit differently, and you don't need to have elevated privileges in order to run a Singularity container or a container with Singularity. And you can run Docker containers with Singularity. So it kind of has a nice set of functionalities in terms of you can still use Docker, but you can use it on an HPC system. Some other software packages that I have not used and that I think are probably in decline in terms of their usership, although I'm not positive on that, are Charlie Cloud and Shifter. Those were also designed for HPC. Containerization has really been, it's fairly new, and so it's been in a state of flux like any sort of new software might be. And so we're seeing kind of, the software of the day for running containers changing, but Docker and Singularity seem to be the two emerging leaders. Any questions? So just reiterates what I had mentioned in the previous slide, that Singularity is what we're using. It's what you have on Teton. It's what we have at CU and CSU. The user is the same inside and outside of the container, so they don't become root or anything else or any other root user. That's really nice on Linux-based systems because you don't have to change your username when you're using the container, and you can't escalate permissions on these. The other nice thing about Singularity is that it can support MPI and GPU resources on HPC. So those of you who have parallel workflows where, say you need to run a climate model or a weather model, you actually can do that. You can actually build one of those models in a container and run it, and people do that. You can use HPC file systems. So when you run a container, it'll typically, if it's installed by your sysadmins on your HPC system, they will have the file systems on your HPC resource automatically mounted already. And if there's any others that they didn't mount, you can mount those at runtime. Supports the use of Docker containers. And then, as I mentioned, containers are seen as a file. So I'm going to give a quick overview of Singularity, and then we'll just dig in and get hands-on so you can see what we have going on here. So I'll cover the typical Singularity workflow, key commands, and then running containers. So the workflow, first thing you'd ask yourself is, do I need a container? So you might need a container if you're having trouble installing a piece of software on Teton or another HPC resource. You're getting library errors, or there may be other reasons. Or if you just want the reproducibility aspect, if you're planning to share this software with a colleague or publish it or something like that. So once you've determined, if you need a container, if you determine that you do, the first thing you want to do is see if the container exists. And I'm going to stop share really quick and stretch this out. Hopefully we can. So I wanted to show you some of the hubs. So this is Docker Hub, and you can search for any number of containers. So you could search for, one with MATLAB runtimes, and there's a ton of different MATLAB stuff in here. If you wanted to search for Python containers, and you can search for specific, Python packages, versions of containers that have Python in specific environments that have packages that you want. So I can't think of anything off the top of my head, but I'm sure there are R containers all over the place. And as a matter of fact, R itself has its own repository that it maintains on Docker Hub. So, so right off the bat, you can see that there's a lot of software so you can search these containers, and then you could pull one of these containers, and we're going to do this in our hands-on, so I'll refrain from doing that at the moment. But you essentially can search for a container you want, and then you can, using the path to it, this is the owner repository is the first part of the string, and then the name of the container is after the slash. So you can actually just pull any of these. So you can search, you can kind of play around and search for other things as well. I think for those of you who I've built some NAMD containers. Actually, this one is one I built. NAMD is, what is that, chemistry? Yeah, there you go. So anyways, that's the point. So that's Docker's repository. And again, Docker is huge. So I have no idea how many containers there are in Docker, but there are tens of thousands, if not millions. Singularity also has its own hub, and Singularity is a smaller community because it's really aimed at HPC users. But you can also search for containers on here. And you can log in. You actually don't need to log in, to my knowledge, but I will log in. Let's see what is. Device verification code. Great. We'll have to use this later, so it's good to log in now anyways. Okay. So I can search for things in here as well. So Python. Sure, there's lots of stuff in here. And so on and so forth. So I just wanted to show you a couple of those that are available. So chances are, in this workflow that I'm showing here, does the container exist? Chances are it may. And so it's worth looking before you go to build one. If it doesn't exist, then you can build your own. And we're going to go over the ways that you build a container in the second half of the tutorial. But your first crack at building a container, you usually do it interactively. You can create what's called a sandbox, which allows you to actually get inside the container and iteratively, you can imagine that it's a trial and error process where you might install something incorrectly or have a command that you munge up. So if you get in there, you can kind of mess up and it's no big deal. While you're interactively building that container, when something works, you paste that command into a recipe file that you're building alongside your interactive development. And then once you're done, you kind of have that recipe as a permanent record of what worked. And then you can automatically build that container from now on. So if you need to tweak something, say you need to upgrade the software in it, a couple months into the future, you now have that recipe file built. And then you're going to run that new container. And so we're going to go through the running next. I just went through this. Where do I find existing containers? Docker Hub, Singularity Hub. There's a new library called Scilabs. So what happened at the beginning of this year was that, or the end of last year, is that Singularity, which was developed at Lawrence Berkeley and Stanford, it spun off into a private company called Scilabs. From a bunch of the people that had developed it at those institutions. So they now, Singularity Hub is still maintained by Stanford, but Scilabs also has their own library as well. So Singularity is, I should mention, even though it's a commercial software company, it's still open source and freely available. And Singularity Hub is free to use. Docker Hub is free to use. Scilabs library is free to use. You can always download for free from any of these. If you want to, If you want to put your repository of containers on any of these, Docker Hub and Singularity Hub are free. Scilab's library is free up to a certain amount of data on there. I'm not sure exactly, I haven't hit that wall yet, but once you hit that, then they have a paywall. So the point is there's plenty of options to run this stuff without having to pay a dime. And we certainly haven't done that yet. University of Utah's Center for High Performance Computing, that's the CHPC in this link here. They've put in some documentation that's kind of nice, a little bit more detailed view of how you might go about finding and running a Docker container that's existing. Okay. Singularity is pretty simple in terms of the commands that you use. It's all command line based. Singularity build, and then some arguments after that will build a container on your user endpoint or in a build environment. So you can build containers either on a system where you have root access. So you can install Singularity on your laptop. And where you have administrative privileges, you can build containers there, or you can build them on a hub. You can't build a container on Teton or another HPC resource where you don't have admin privileges. So what I'm going to show you today are ways to build containers where you don't have root access. But if you wanted to just kind of have full-on ability to interactively develop a container, then you could install Singularity on your laptops. Tim has actually developed a really nice install script for getting Singularity onto your laptop, if I recall correctly. Is that right, Tim?
Yeah, it's a virtual machine which gives you the root.
Okay.
Yeah. So, I'll actually point to that.
Okay, that's great. Singularity exec is how you execute a command in your container. So essentially, once you've built a container or pulled a container down, say the container name is my container, you type Singularity exec my container and then the command in that environment. So it might be Python and then some Python script that you've written. Inspect just lets you see what's inside the kind of what's under the hood of the container. So you can see how it was built, what environment variables are in it, that type of thing. Singularity pull is how you grab an image from one of the hubs that I just showed you. So from Docker Hub or Singularity Hub. Singularity run is a lot like Singularity exec. Singularity run is if a user built a container and they want that container to be run in a very specific way, they can put a script that is the default behavior of that container. So we were talking earlier about a software pipeline. So say you have a software pipeline that your typical user is not going to want to have to think about running 10 different pieces of software in order, but you could write a script that runs those 10 pieces in order. And so you'd install that software in the container, and then you'd write a little wrapper script. And that wrapper script would be the default thing that's kicked off in your container if you type Singularity run container name. And then you can shell into the image, which can be useful when you're trying to troubleshoot issues. Like oftentimes you might not, there's an environment variable that's missing from the container, or if you're trying to read a file and you can't see it, and you want to see what the external environment, what the file systems the container can see are, you can shell in and then look around just like you would in any Linux environment. Questions? All right. So Singularity pull is how you grab images. And to get something from Singularity Hub, it's Singularity pull SHUB, shub for Singularity Hub, and then the repo name and the image name. So the repository name could be my name, for example. So these hubs, you can create your own repository on there. What you'll typically do is log in with your GitHub account. So if you don't have a GitHub account, I'll have you create one at the break, but it's free to create a GitHub account. So my GitHub user account is my last name. So that would be my repo name in Singularity Hub or Docker Hub. and then the image name is the image that I built up on that hub. Um, Same thing for Singularity Pull Library. That's the Scilabs library, and then Singularity Pull Docker, and then the repo and image name. So they're all similar nomenclatures, but you have 3 different repositories that you can pull from. I think there are some other repositories as well that there's functionality for. Docker Hub and Singularity Hub are really the main ones at this point. To run the container, go ahead. We have a question.
When you pull Docker images or images, container images, any different functionality
You can pull, um, so GitHub is where you would stage the recipe. So if you want to build a container on Singularity Hub or Docker Hub, what you can do is you create a recipe, what's called a recipe file, but that's kind of the instructions on how to build the container. So it'd be like, apt-get install X, Y, and Z packages, compile my software, set some environment variables. Essentially what your container is going to look like is built off of that recipe file that might be anywhere between 2 and 100 lines, depending on the complexity of your container. So you have that recipe file. What you do is you log into GitHub, or are you a GitHub user? So you'd push, you could create a new repo in GitHub under your username and push that recipe up there. And the recipe is going to have a specific name. It's going to be Docker file if it's Docker Hub that you want it to go to, and it's going to be called Singularity if it's Singularity Hub. Then you can just log on to Singularity Hub and Docker Hub with your GitHub credentials, and it will find that recipe file and build that container in the cloud, and then place the container on the hub, and then you can just download the container from anywhere. So that's kind of how that would work. So the container itself wouldn't, to my knowledge, I've not seen any containers hosted on GitHub, in part because GitHub has a maximum file size of 25 megabytes. I think unless you have a pay account. And so most containers are bigger than 25 megs. So you're essentially just hosting the information about what's needed to build the container rather than the container itself in GitHub, and then using Singularity Hub or Docker Hub to grab that recipe and build and host the container. I'm sure it could. I would imagine you could do that. I actually have not experimented with that. I would hope you could do that. So. 1 gig for free? Okay. So you're pushing the limits of my knowledge of how to do this. So you'll have to try. Tim?
put them on any place, once you have the container built, any web page that you have access to, public access to, do a kernel or stuff you get, or they don't have to be on these specialized websites.
Yeah, Tim noted that the recipes don't have to be on these specialized websites, but I think that if you're going to build a container on Singularity Hub or Docker Hub in the cloud, that you would have to have it in some sort of GitHub repo.
Yeah, but you could, even then, you can download that to your local web server.
Good point. Yeah. So.
I don't know if there is you said good point. I'm not sure there is a.
Well, yeah. Maybe that there's many ways you can do this, and I think some of it's a little bit trial and error. I'm going to go through an example today of building a container remotely on Singularity Hub, and that's why I was asking you all to get a GitHub account, because we're gonna create a GitHub repo in your personal account, and then we're gonna log on to Singularity Hub and essentially grab that recipe file and have you build the container. You can shell into an image, Singularity shell, my container name, and then inspect an image. So if I wanted to see what the run script was, if someone had put one in, I could Singularity inspect, and then -- run script. Okay, let's get to the hands-on here. So if you are online via Zoom, You do not have access to the temporary accounts. However, if you have an account on Teton, you can log in as you normally would via a terminal, some sort of terminal or terminal emulator. For those of you in the classroom, you do have temporary accounts. And did we pass out the okay. So you have a UB key with a username on it. And I think mine's 24, was it? Okay. I'll figure it out. And so let me bring up. No, yeah, absolutely not. And if you're on a Mac or if you don't have to use we're going to use MOBA Xterm because we're all on Windows machines in this lab. That's one of many terminal emulators. But if you're on a Mac, you have a terminal app already installed on there that you can use. And if anyone has any trouble with this step, let me know. But I'm going to show those in the room how you would do this. So for MOBA Xterm, we're going to start a new session. And so it's going to bring up this screen. And we're all going to have the same remote host name. It's going to be teton.uyo.edu. And then your username is going to be the username on the side of are these YubiKeys or whatever? And I think mine's ARCC-T24. So yours is also going to be ARCC-T and then some other number. And then you're going to hit OK.
Okay, so this is where I move the board here.
And there's a password on the board.
Yeah. So the password is Northgate, capital N, capital G. So capital N, 0, R, PH, capital G, @ TE. And then it'll be,
then once.
You didn't read the instructions above you. So you do the password, and then you hit a comma, and then you push that button on the UV.
Okay. Got it. Try again here. And
So don't hit enter, just push the button. Yeah, yours is.
all right.
Yeah, no, come after password, then hit the button.
If anyone online is having any issues, let us know. And again, if you don't, you'll need to have your own Teton account if you're participating via Zoom. The temporary accounts can only be used within this room because they require a physical device for two-factor authentication. But if you are having any issues and you do have a Teton account, then let us know.
Anybody else having issues? Oh, let's try new one.
Everyone else was able to log in? All right. Can you see this back there? All right. The text is big. I'll try to blow up the text a little bit on that. I can figure out. Okay, for those of you who have logged in, as a next step, we're going to have you start an interactive job, what you're doing here for those of you who are not HPC users is you'll be getting you're kind of getting your very own resources on which to just run the containers so that we don't overwork the login node. So the way that you start a job, and those of you on Zoom can do the same here, is the way we start an interactive job is SELEC. Then we're capital A for account, and we have an account for this course called Arcane, ARCC, ANETRANE. So ARCC, ANETRAIN. And then we're going to set it up for 150 minutes, which will hopefully, if our terminal doesn't time out, it'll just get us through the rest of this this session. You could probably do 120 as well, since we'll be done by noon and it's about 10. So T, and then I'm going to do 2 hours, 120 minutes, and then want you to have 2 cores. So that's dash in 2. The reason we want 2 cores is we're going to test run an MPI-based container today, so I wanted you to be able to run it on multiple cores. So SALEC dash capital A, Arcane train with 2 C's, dash T, 120 or 150, whatever.
If you're using your own login, you won't have access to this Arcane train. You have to use your own project name.
Okay. For those of you on Zoom, use your own account or project name instead of Arcane train. And 2 cores. All right. Okay, great. And you'll know that you're on you can see that your prompt changes from being on tlog1 to one of the compute nodes. So I'm on M071 here. Okay. How many of you in here use Teton or have HPC experience? Okay, so most of you. So for those of you less familiar, the way software is managed on HPC systems is generally through modules. So you don't always have some of the key software packages available to you immediately. You need to load them, and so you do that through modules. So we're going to type module load Singularity. Then we're going to use, I think you could just type module load Singularity and you'll get this version, but I'm going to just, for completeness, make sure that we get version 3.1.1. And it'll tell you that it's been loaded. And I want you to export an environment variable called Singularity Temperature, all caps. And I wanted to set it to your gscratch directory, which is /gscratch/ all. You can either type your username or just type $, all caps user. The reason we're doing this is an environment variable that's recognized by Singularity. By default, when you build containers, Singularity will use the temp directory on a given system, on a given node. And if we have a bunch of us, I'm a little worried that temp is going to fill up. And so this way, we're kind of creating a large relief valve where you can place your temporary information when you build containers. And you can always echo Singularity Temperature to see what the value is. So you can see that it took on the value of my username, which is ARCC-T24. And let me know. I can blow this up just a hair more. All right. Anyone still working? Happy to wait. Okay, great. So now we're set. Let's download this GitHub repository now so that we have it. So go ahead and let's go. You could do this from your home directory, but let's just go to gscratch and your user directory. So if you type pwd, you should be in, after you've done that cd, you should be in gscratch and then your username, whatever that is. And is okay. I was just seeing if Git was available. So you can git clone and then https github.com research computing, all one word, and then UYO 2019. Sorry, I should have done a bit.ly address. I apologize for making everyone type this. Well, that should clone this in a couple of seconds. If you had any issues, let me know. I'll help you out. Everyone get it? Okay. So if you type ls now, you should see that directory in there called UYO, and go ahead and cd into that. Type ls. And this is just the same repo that you could browse in your web browser, but it has the slides, the PowerPoint that I'm presenting on the left here, a PDF version of it as well. And then there's two directories we're going to be working in. This first, the one we're going to do now is called Run Singularity Basic. You can go ahead and CD there. To be honest, you're not really going to need to use anything in here. If you get behind or want to go through this tutorial later on and you don't want to have to cut and paste from this PowerPoint, the tutorial steps.txt file, you can cat that and it has everything that we're going to do here before the break. Just kind of a list of the commands so you could copy and paste things if you wanted to. In any case, that's all that's in there. I also put in, I'm going to do an example of an OpenMPI container on Teton, and I put in an OpenMPI recipe file you could use as a template if you wanted to build MPI-based applications on Teton. So it actually will work on this specific system. Okay. Tutorial steps.txt. And then it's kind of, because I have this thing blown up so much, it doesn't display very well, but you could, yeah, you can type more tutorial steps. So
Just for reference,
yeah, good point. Good point. So, and this is the same text that's in my slides on the left here is just in this thing, so that make it a little bit easier for you. All right, so we're going to go ahead and pull our first container and run it. So we're going to pull a container that I built beforehand. That's kind of a hello world type of container. The name of it is terrible. I should have made it much shorter, but 2020 hindsight. Singularity. And you can paste this in if you want, or you can type it out to get familiar with it. Singularity poll. So as you can see, everything you do with Singularity starts with Singularity and then some command and then the arguments to it. Singularity poll. We're going to name this. I think you can forgo the name flag, but you can also, you can call it just hello.sif, or you can use the name flag. Shub. Singularity git, whoops, tutorial. And you'll get a warning, that's no big deal. Yeah, good question, and I'll go over that a little bit in the second half. But it's a compressed file format that is immutable, meaning you can't modify it. Singularity uses it. It's actually a squashfs file. For those of you who are familiar with squashfs, I think it's kind of your standard cell phone compressed. It's a very good compression file format, so you can just make things small on it, but you can't modify a file that's in that format. Did everyone have success? So if you type ls, you should see a file called hello.sif in here now. So that's your container. So these container names are all going to end in .sif, Singularity image format. Even if you pull a Docker container, what essentially happens during that pull is it converts the Docker container to a Singularity container. So you're going to want to name anything you pull a .sif file. So let's go ahead and run that then. I had a default run script to run this. So Singularity run hello.sif. And it's got some bad grammar in it, I think. This is run when you run the image, and it says hello world, but it works. Did everyone have success with that? All right. And then we can, so if I type Singularity inspect run script hello.sif, it'll tell me the script that it just ran when we did Singularity run. And you can see that it's I'm essentially executing executing it this way. So we can look at that. So there's a script in a subdirectory in the container called hello. Subdirectory called code, and it's a script called hello.sh. So I could type, if I wanted to dump that, like see what's in that script, I could type Singularity exec hello.sif, then cat, which is the command in Linux to dump the contents of a file to screen, and then code hello.sh. And that is literally all that's in there, one line. It's not even a proper bash script. And you could run this container as well with exec, Singularity exec, hello.sif. And then I think if we put this in, whoops, it is okay. Ah, got it. So it didn't have exec. So I may have, there we go. So just type. So the point there was, I know this seems a little weird, but so the first thing we did when we downloaded this was we just used Singularity run hello.sif. Let me bring this out a hair here. And that ran the default run script that I had written when I installed that. I may not, as the container person who built the container, I may or may not have built a run script. In this case, I did, but a lot of times I may not. In that case, you can use Singularity exec to run whatever you ran in the run script. It's just that you're kind of manually doing it. And when you use Singularity exec in the container name, what you can kind of think of this is everything after Singularity exec container name is what you would type if you were just going to run this at the command prompt on your machine. So in this case, we're executing cat code hello sh within the container, or we're executing the actual script with the bash shell. So Singularity exec container name, and then all the commands you would normally run if you were just going to not run it if you're running it somewhere other than a container. So you actually can, a lot of times I will, the reason this is kind of useful to know, if you're creating a container that you just don't want to deal with all that preface Singularity exec container name, you can create a wrapper script that essentially would, a bash shell script that you just type like one word to the name of the shell script, and it will load, in that shell script, you'd have module load singularity exec load.sif, and then an @ symbol for any arguments you feed to it. And then you can type that wrapper script name and the arguments you want to feed to after that. And it would be essentially identical to just running it from a command line. So you could essentially abstract the fact that you're using a container, is what I'm saying, by wrapping up all this nomenclature inside there. Okay. Questions? One question.
How do you make sure that it's safe to run in the image for that? I mean, there are some commands with vendors. How do you know?
Tim, do you have any thoughts? So for those of you online, the question was, how do you know if it's safe to run a container?
No, I don't. I never thought about that.
Yeah.
You have containers, doesn't it?
Yes, you can. Some of those have popped up on Docker Hub. Singularity, now that they've gone private, what they're promoting is a kind of a trusted signature from the container builder. So you would essentially verify before you ran it that it came from a trusted source. But at the moment, to my knowledge, that's really the only way. So if your colleague gives you the container and you trust them, it would be considered safe to run the container. Or if it's a trusted repository on Docker Hub, for example, we saw that there were some containers that were maintained by R or by Anaconda or some software company, you probably wouldn't trust those. I don't think you can really get away with, that I know of, running nefarious commands from a container, just because your user, you have the same privileges inside the container as you have outside the container. So it's associated with your user namespace. So you could try to nefariously run the container, and so for example, if I type singularity exec low.sif sudo ls, sudo is not even found, so it's not even an option in this container. Sudo might be in a given container, but you're not going to have permission because you're just you and not root. That's a good question. I need to be better prepared to answer that in the future. Okay, let's pull a Docker container. So in that example we just did, we pulled a container from Singularity Hub. We can also pull one from Docker, which would probably be more common if you're using pre-existing containers. So you can use them on Teton. So right now, as a matter of fact, we're going to pull a Docker container from Docker Hub onto Teton and run it. Just to create a container, yeah. Thanks for asking that. So for those online, there was a question about, what you can do with a container where, depending on the permissions you have. You can run a container without administrative privileges anywhere. So you can pull a container from Docker, from Singularity Hub, and run it on Teton. What you can't do without root access is build a container on a given HPC system. If you want to build a container, you can either build it remotely in the cloud using one of the hubs. So you can log on to Docker Hub or log on to Singularity Hub and pull the recipe that you posted on GitHub. So you build a recipe for a container, you post it on GitHub, and then you can log into any of the hubs with your GitHub credentials, essentially your GitHub account, and then it will find, or you can help it discover where that recipe is in your GitHub account, and then it will kick off a remote builder in the cloud. And it'll take, depending on the size of the container, it might take anywhere from 15 minutes to an hour, depending how big the container is. It'll build that container. When it's done, then there will actually be a URL to pull that container, and that's actually what we're doing here. So for example, in the previous example, we pulled a container from my repository on Singularity Hub called, Monahan, and then Singularity Git tutorial was what I named that container. I built that container. If you logged on to my GitHub account, you would see that I have a recipe file for that container in there. So I had just put a recipe up in GitHub, but let the hub build the container. So that's, I know that's, I'm not articulating this well, but what I mean there is that if you want to build your containers on the hub, you don't ever need root access for anything with the container. You can just use Singularity that's installed on Teton, and then you can build up on one of the hubs. If you want to have a really interactive container build experience, like if you just don't know what you're going to need to do to install it, your best bet there is then to install Singularity on your on like your desktop or laptop machine, somewhere where you have administrative privileges, and then build the container on there. And then you can either upload the container to Teton, or you could create a recipe based on that interactive build that you did, kind of the final set of the correct commands you need to build it. You could post those on GitHub and then have either Singularity Hub or Docker Hub build that container for you. Okay, so this was the example we just did where we grabbed a container that I'd built out of my GitHub account. Here we're just going to grab an existing container. So literally, what I would do here, I want to just show you kind of the process here. So there's a container on Docker Hub that I found. I searched for what I wanted was a lightweight Python container in this case, and I found this one called tinycore-python that's in this user's directory. So what I'm going to do then is pull that container onto Teton and run it. And the way I can do that is just Singularity pull. And then if I want to name the container something other than the default name, I can give it a name. So I'm going to call it Python d.sif. And then I'm going to shrink this window up just a hair. Python d.sif. And then Docker. So the name of the repo and container that I discovered by browsing Docker Hub, I'm going to grab the container from that. And you'll notice that the build looks a little bit different from pulling from Singularity Hub. Docker stores images in layers, whereas Singularity stores images as one big chunk. And so when you pull a Docker image, it's a little more verbose, but it's the same basic result. So this is done now for me. And if I ls, I can see that I now have a container in my directory, and called pythond.sif. And again, the command I used for that was Singularity pull, and then I used --name to name it pythond.sif, and then Docker to indicate that I wanted to pull it off of Docker Hub, // and then the person's repo name and the name of the container. I don't think so. Let's see the command. Let's see. File not tiny core dash. Oops, can you put that? Wonder if something got munged in the
I wonder if you already did it.
Did anyone else have issues pulling this container? Um, G scratch arc. Okay. Where are we here? No such. It's an interesting error. G scratch. You don't have to have that. It just helps. I was trying to simplify this down to nothing. I'm not sure why everyone else is. Yeah, let's move to a different directory and see if that works. File not found. Authentication to. I don't think you should have any issues. It doesn't. Yeah, it's agnostic to. You don't need an account or anything to pull. So maybe you could try to pull a different Python. Okay, you're having an issue. I'll move on in just a moment here. Okay. I actually probably don't even have any. Okay. Seems to be a system, like a specific to his account.
It's a training account. Yeah, have the same as everybody else. That's a weird one.
We could try to log you in as somebody else. Okay.
All right. Do you want to answer that? Oh, okay. Mike is already doing it, but.
What was the? So I pulled the Python image from Docker Hub and Singularity rebuild gives me the warning. Building containers on this. Yeah, that's okay. Yeah. Yeah. So for those, there was a question online about the warning sign that you get when you're building a Docker container, which is my buffer isn't big enough to do, but it essentially warns you that you're building as a non-root user. So remember the typically Docker containers are run with some sort of administrative privilege on your laptop or desktop or somewhere else where you have root privileges. On this system, you don't have it. So it's essentially warning you that when you download a Docker container using Singularity, that you may not have the full functionality that you'd have if you ran Docker. The reality is that that's typically not true if you're just downloading a Docker container that has a piece of software that you want to run. So you can essentially ignore that. Okay. So let's, you may have gotten ahead of me here, but let's just Singularity exec. I'll widen this out just a hair here. So let's type the second red command on the slide, Singularity exec Python d.sif, so the container name, and then let's type Python. And you actually get a prompt. So you're actually running Python from within a container. So you could think of this in terms of if there are, if there's a version of Python you would need that doesn't exist on a given system, you could actually create a container that has that specific version of Python, those specific Python packages that you want, and then you could actually run that from the command line if you wanted. You can also run a script if you have a script, and we'll do that in a bit. So I'm going to exit out of here. So now I'm back to my command prompt. Yeah, if you were going to run a Python script, you just do this, and then you add your, script name .py. I don't have a script right now, but if I had one, it'd be there. So the script does not have to be in the container. The script is actually outside of the container typically, unless you had like a script that you were publishing as part of a paper, or that you just didn't want someone modifying. You could put it in the container if you wanted. That is right, and you can check that. So if we type Python version from the command prompt, the base kind of stock Python on Teton is 2.7.5. And if we module spider Python, you could also load a Python module. So you have 3.6.3 on here as well. So if you wanted, so you have Python 2.7.5 as just kind of your default. You could load the Python 3.6.3 module on here. If you wanted to use a different version, you could do it in the container. We can check the version if we do a Singularity. Let's see here. Singularity exec Python version. So it's Python 3.6.0 inside the container. It's a good question. So so think of these first three words: Singularity exec Python d.sif. That's what you need to do to tell the system that you want to run something inside the container. So you're saying, I'm invoking Singularity. I want to execute a command inside a container named Python d.sif, and then everything comes after that. So if you were outside of the container, think of it as like the three words that you have to run something in a container, but everything else would look exactly like it would look if you were just going to run it at the command prompt on the system in C2. So, if I just wanted to run the system Python, I'd just type Python version. If I want to run the container Python, then I need to type Singularity exec Python D and then Python version. Just as you would at the command line. So if I had, I do have so if I VI, test, if I create a script called testscript.py and say print so I got this Python script now that I want to run. I can run it at the command prompt here on this system. So this is the Teton Python, but I could also do it with the containerized version of Python like that. So in this case, it doesn't matter, right? It's just running Python on a really basic script. But if you had some special Python packages you needed to import that weren't on Teton, but you had them installed in your container, that would be a reason why you would want to run the container. So you had some special Python functionality or a version of Python that you needed. It'll work. Yeah, you're going to want to put, I actually have a slide on that later, I think, but essentially you're going to want to, so when you invoke a container, do you know what PWD is on Linux, present working directory? So you have an environment variable called PWD. So if you echo that, it's going to tell you the directory you're in. So right now we're in run Singularity basic. PWD is automatically mounted when you run the container. So if we shell into this container, which we were going to do next anyways, Singularity shell python-d.sif, and I ls, look what it shows me. It shows me PWD. And if I echo PWD, it shows me that I'm on G-Scratch. So it actually is, you're actually, even though you're in the container right now, and you can tell that because the prompt says Singularity in this case, even though you're in there, you're mounting the file system on here. However, the container does have some of its own, it does have its own file system. And so that can be a source of, you're asking a really good question, because that can be a source of confusion. You know, when you create a container, you're essentially, the first thing you're doing is you're creating your favorite flavor of Linux. So like Ubuntu version whatever, or if you like Debian or CentOS or whatever version of Linux is your favorite, you install that as your base, kind of the base layer of your container, and then you put in all the software that you want. And so just like any Linux system, it has the base of your file tree that has a user directory and a user local bin. It has a root directory. It has a mount directory, a lib, and then there's the directories that are mounted on the system, and those are going to be. I know that G-Scratch is not in my container, but it's a thing on here. Home is automatically mounted as well. So I'm going to see all the users in the Wyoming home directory. And if I wanted to see my home directory, I don't have anything in my home directory, but if I echoed home user, it's my username, so it would go to my username. So the point I'm making here is that you do want to be a little bit careful. So if you would have you would probably install usually in containers or anywhere on Linux the OPT directory. So if you /OPT, and I'm assuming OPT is not auto-mounted on here, but I'm not positive. It's okay. Usually OPT is where you want to do something, or when you build a container, you can create a directory called code or files or scripts. And then you would specify something that you know is not on the host system. So for example, in that earlier example I ran, the first example I ran, I had a code directory. I knew that there would not be a /code directory on Teton, but so I could easily throw stuff in /code and know that when I run my Python, if I had my Python scripts, I could put them in /code, and then I would, I'm gonna exit out of here. Then when I run this, I could, if I had testscript.py in the container, I could have thrown it in a directory called code. I could call this thing anything I wanted, right? I could call it foo or bar or whatever I want. But it's just as long as I created it when I built the container. So just a unique directory path that you know is not going to be on any host system that you run the container on. That's what I would recommend you do. There is. Yeah, so put it in a non-standard, like just create a uniquely named directory that you know is not going to be in the root of a typical Linux directory.
Does it prefer what's in image and then what's in the layer above, like Teton? So it goes from.
It's going to use yeah, you can, I actually go over bind mounting, but you can, we could actually, so this is interesting. So if I shell into this container and I look at sbin, there's a bunch of stuff. This is inside, this is the sbin directory in the container. If I exit there, I'm going to Singularity, see if I can do this right. Bind. home user. Now if I ls sbin, it shows my home directory, which I don't, it's a bad example because I don't have anything in my home directory, but maybe if I ls-a, okay. Now I can see all the stuff in my home directory. So I just mounted an external directory to a completely different named directory in the container. So you have a lot of flexibility for that, but that gives you, like, hopefully that demonstrated that, you know, in the container, the sbin directory, which I knew was a standard Linux directory that you're going to get if you install any Linux system, I knew that that would be, you know, specific to that container, but I could overwrite that by bind mounting from the outside. So what happens is that the folks who installed Singularity on Teton, they in the config file can specify auto bind mounts things. So I just manually bind mounted this thing at the command line with that bind flag right there. Essentially, they've already done that for a bunch of directories on the Teton file system. So those are going to take precedent over like the home directory in the container. The home directory on Teton took precedent over that. And we saw that when we ls just /home, we saw all the users on the system. So that's a case. So always anything bind mounted from the outside, if it has the same name as a directory inside, it's going to take precedent. So when you store code in a container, what that means is that your best bet is to create a completely uniquely named thing, like, you know, supercalifragilistic something, and then put your code in there, and then you know that you're never going to have a conflict. All right, I think we will take a break here, and we already did this. We just created a test script, right? And that was my next slide, was to just create like a hello world script. In this case, I called it myscript.py, but I just did the equivalent thing in that previous exercise, just to show you that you create a Python script from the outside. Running an MPI container. Actually, let's do this really quick. So go ahead and pull this, because this is the last thing before the break. Paste. All right, thanks. Yeah. So I want you to pull this MPI container. And all I want to show you here is how you run a container that, if you have a piece of code that's parallelized, so like a weather or climate model or something else that needs to exploit multiple cores, you can do that in a container. And I've created a container that does that for you. And I want to show you how to do it. Okay. All right. So I now have a hello openmpi.sif container. Does everyone have that? Okay. Now what I want you to do, in order to run how many of you have run parallel codes on anywhere before, Teton or elsewhere? So the way, for those who are less familiar, on an HPC system, what you're doing when you run a parallel code with so there's two ways to run parallel codes. There's what's called shared memory parallelization, which is what you might do on your laptop if you're running Python or R. You may not even know you're doing it, but if you have a given computer that has multiple cores, so you have like a 4-core CPU on your system or an 8-core CPU on your system, you can use threading in order to parallelize that code. And it's all reading from the same memory because you just have a hard disk on your laptop. If you need to scale up a big code on an HPC system, you may need to scale it across more than one node. You can think of a node as being an individual computer that has, within that node, there are multiple cores and they have access to a shared memory. But if you want to run your code across 2 or more nodes, then you have the issue of needing to have some sort of distributed memory. So that's called distributed memory parallelization, we use what's called MPI, message passing interface, to set that up. And your HPC system is going to have MPI libraries on it. When you're running containers, you're going to need to load those modules. So it actually needs to find those libraries on your system. So I have on this PowerPoint slide, you'll see that there's some module load commands in order to get this on. So MPI is always dependent on a given compiler. So the first thing we need to do is load a compiler. So we're going to module load GCC. We're going to load 7.3.0. There's a bunch of different GCCs on here probably. So GCC is just GNU's C, Fortran, C++ compiler. And then we're going to module load swset. And then you can load OpenMPI 3.1.0. So this is now going to allow you to parallelize. So now we can MPI. If you haven't run a code before with MPI, it's pretty easy. You essentially just preface whatever you were going to do otherwise with MPI run and then the number of cores you want to parallelize on. So MPI run -n for number of cores, 2. And then let's just run that same Singularity exec hello openmpi.sif. And then inside that container, I have compiled a piece of software, a little executable called MPI hello world. And it runs. So, and it reports back hello world from the processor that it was running from. Did everyone have success?
Now, what if I don't have the OpenMPI on the host and I want to use Singularity to run it?
You'll have to install OpenMPI on the host, and that will be something that, if you're on an HPC system, that is one of the most basic things you will find. So you'll always find that on an HPC system where you would be doing this type of thing. Yeah, so that's a good point. Okay, we showed you how to bind directories in a previous slide. I just wanted to give some notes on MPI containers. So it's still early days, I would say, for MPI. So at the beginning of this talk, I told you that reproducibility and kind of being able to, and portability is one of the major reasons you want to use containers. When running MPI-enabled apps, containers haven't quite made it to that point yet. And in particular, they're dependent on a couple of host system things. There's 2 things. One is that they typically need to be running the same major version of MPI as you're using on the system. So before I built the container for this tutorial, Dylan helped me figure out what versions of OpenMPI you have available on the system, and then I picked one. I picked the one that we loaded in that previous slide, which was OpenMPI 3.1.0. And that determined why we loaded GCC 7.3, because in order to load OpenMPI 3.1.0 on this system, it's built on top of GCC 7.3. So really, the decisions to load all these modules on here were based on me selecting OpenMPI 3.1.0. What I did then was I built the container that we just pulled using OpenMPI 3.1.0. So that's a prerequisite. It doesn't have to be usually the same minor version, but it has to be the same major version. I think this will change. So, I mean, the whole point is that these are portable, right? And right now you're kind of violating that. But I think that there are still some issues with how MPI libraries are developed that cause these problems. The other thing that you'll want to do, this is optional, but if you want to take advantage of the high speed, low latency fabric that's on the system, so the fabric is the cabling that connects the nodes when you're going to run across jobs across nodes, parallel across nodes. InfiniBand is what is used on Teton. So you can you also need to have those libraries in your container. If you don't really care about that and you just want to use Ethernet, then you don't need to worry about having those libraries installed on there. But your node-to-node communication is likely going to be slower because of that. So if you want to take advantage of the low latency message passing between nodes, you'll want to find out from your, it's usually in the specs that are listed on the website, and that's where I found it for your machine, your wiki pages. But InfiniBand is pretty common these days. And there's a, was it libib verbs or something that you have to install in the container. If any of you have questions about that specifically, either ask me at the break or afterwards, or just email me. I know that these are, the MPI stuff is a little more nuanced, and I'm very happy to help you build an MPI container. The template that I put in the directory in the GitHub repo is specific for Teton, and it will work on this system. Yeah. Yeah. Does anyone use GPUs? Okay, sometimes. NVIDIA has a fantastic container building tool that will build just about any app for you these days. The main thing about running across GPUs is Singularity now has an NVIDIA flag. So most GPUs, including on yours, are NVIDIA GPUs. If you use, you can see on this, there's Singularity exec --NV. What that essentially says is that you don't have to have specific driver libraries installed in the container. So for those of you who use GPUs, you'll know that you've probably encountered an issue with driver library versions before. These are the versions of the driver libraries for the GPUs that are installed on that GPU node, and they're different on every system. And compatibility with those libraries can be a challenge. So what they've essentially done in Singularity is said, don't even bother with the NVIDIA, like trying to match up your libraries in the container. Just use the NVIDIA flag when you run the container, and use the host's driver version. The one caveat to that, for those of you who use GPUs, CUDA, which is how you develop code for GPU applications, it has different versions, and there is the version of the driver has to support a given version of CUDA. I put in a link here that will give you a table of compatible driver versions and compatible libraries. You can get onto a GPU node here, or just send in a help desk ticket and find out what the driver version is, and then you can build your container so that you have a version of CUDA in that container that's compatible. Again, if you have questions, feel free to ask. Okay, now it's the break. Okay, quick review, Singularity poll from any of those hubs. Any questions on that? We didn't do the Scilabs hub, which has the library preface to the repo name and image name, but we did do Singularity hub, which is shub, and we did Docker. So that's how you can grab an image, either a public image that someone else created, or if you built an image on one of the hubs, which we're going to do an example in this session, you can pull it that way. To run a container that has a default run script, Singularity run container name. To execute some specific thing in the container without a run script, just as you would at the command prompt, you preface that command with Singularity exec container name, and then whatever commands you would run at the command prompt.
One online question. Question is, so correct me if I'm wrong, but are containers analogous to Python Anaconda environments, but on a larger scale and Linux-based?
Not particularly. You can install Conda environments within containers, and that's a good way to build complex software pipelines for some applications where there's a lot of, say, Python packages. Conda is a package manager that will allow you to install things on a given system, on a given host system. A Conda is actually more analogous to the module stack, I would say, on the Linux system. It's really a way to install a bunch of software, and it does its best to avoid conflicts between shared libraries that might be being used by multiple versions of software. But it does, I think your question is probably, you're creating a self-contained environment in Conda, and isn't a container like that. It is in that respect, but I think what you'll find with the containers is that the containers are portable across systems, and you can run you can build a container with your favorite. You can choose what environment you want that container to be. So if you installed Conda in a container, you could pick your favorite version of Linux, and then you could just move that container around to different systems and use that exact same Conda environment in the container. Whereas if you just use Conda install on the host system and you move to a different system, you'd have to install that same environment. And it may be challenging to do, particularly if it's a different, if the version of Conda changes, if there's been updates to packages behind the scenes, or if you're on a different architecture of system. So there are some similarities, but I would say containers are a little bit more flexible and would supersede Conda in that you can install Conda in a container. You can shell into a container, and you can inspect a container as well. So that was just a quick review of what we can do. And those were the things that we did in the last session. Now we want to get into building a container. And I alluded to this previously. In my view, there are 3 ways to build a Singularity container. The most basic way, and this works quite well, is to build a container on a system on which you have administrative privilege. This is typically going to be your laptop or desktop machine. The pros of this are that you can interactively build the container. When I say interactively build, what I mean is that a lot of times you can just kind of find someone else's recipe who built a similar container, and then you modify it a little bit. You don't really have to interactively build. You can just keep using the recipe to build a container. But sometimes you want to kind of build it from scratch. You want to actually create what's called a sandbox, or a basic container, shell into it, and then start installing the packages you need, because you're not quite sure what the recipe should be. And then as you get things right by trial and error, you'll build up that recipe file. Think of that recipe file as the permanent record of how to build that container that is then what makes it reproducible when others, if you need to rebuild it again, or if others need to build it from scratch. So in order to do interactive development, you need to have root access. And so that's going to require that you do it on your system. The other thing with building containers, in my view, on your base system is that you end up with a big file on your laptop. Sometimes they can get into the gigabytes if you're, depending on what you're doing. And then, A, you have a big file on a small hard drive on your laptop, and B, if you want to use that on an HPC cluster, then you need to upload a 2 GB file, and you have the latency of the file transfer to deal with. So, there are definitely pros for like at the very beginning of developing a brand new type of container. Otherwise, I think these second 2 ways of building containers work really well once you have a little bit better idea of the type of container and you have a recipe for it. So building a container on Singularity Hub using a recipe, and those containers of mine that you downloaded in the previous session from Shub and then the Monahan repository, those were ones that I used this technique for. I had a recipe, I put it in my GitHub repo, and then I built it on Singularity Hub, and then it was available from anywhere where I wanted to download it. So the pros there are that you don't have to use any disk space on your system. You don't need to have administrative privilege. You don't need to install Singularity on your laptop. And it's easy to retrieve from anywhere. The cons are that you can't do the interactive development. So if you know it's going to be a trial and error process and something's going to go wrong the first 10 times you try it, then that can be a little bit frustrating. The other, go ahead. That's a perfect example. I mean, those are, as you know, like you're probably going to iterate on something 50 times before you get it right when you're building a complex pipeline. And in that case, you probably just want to put Singularity on your laptop. And it's not that big of a deal to put it on your laptop. It's just, um, um, yes, yeah, you can. And then the third way is a kind of a brand new way as of this year. So Singularity Hub is to my knowledge is going to perpetuate into the future. It was built when Singularity was still a publicly available or was not a private owned by a private company, and it's managed at Stanford. It's the services provided by whatever Google's cloud service is, and they just sent out a survey to users asking what users wanted to do with it. And I don't know if you got that, Tim, but they've now upgraded it so that it builds containers with Singularity version 3 as well as version 2. So I think that means that they're going to keep it. I was a little worried that it would disappear when Singularity was spun off to this private company, Scilabs. Because Scilabs now, this third method is that there's a remote builder. And I'll show you a demo of this, but I'm not going to have you do it because we don't have time to all run through that today. But Scilabs has a remote builder as well. And you can either paste the recipe onto their website into a little box and it'll build the container from that, or you can get a token from their website, paste it into your home, a file in your home directory on Teton. It'll give you essentially like passwordless access to their remote builder. And then you can actually build from Teton. The resulting container will show up on Teton, be placed on Teton. So it's a really nice feature. The cons from that are the main one is that I know that it's kind of a freemium version. So at some point, if you build too many of these, and I haven't hit that limit, you're probably going to hit a paywall. But I think it's definitely worth considering because it's super easy to use. Mm-hmm. Tim?
Yes. Okay. Well, it's sort of. And that's basically how I build most of my stuff. I actually have a virtual machine on my Mac, and the same problem. So I have a virtual machine in which I have Singularity installed, and then I do all my stuff there. And this afternoon I'll actually show you the tweet mentioned earlier. How I pay for all that stuff. That's awesome. Yeah, very cool. I can even give you my virtual machine if you want.
Okay, so those are our three ways, and I'm going to emphasize, since I don't want to go through the process of having you all install Singularity on your, well, you're all using public resources anyways, but we're not going to do the build from scratch on your laptop today just because of the hassle of everyone having to install it. But I think you'll have the fundamentals to do that based on this. I do show how to do that. But kind of the basis for a container is this recipe file. So what is a recipe? This is a recipe for an entire container. So it's a few lines. You can have much longer recipes, but really at a minimum, you could have 2 lines in a recipe file, these top 2 lines. So you're going to bootstrap from Docker. What that's saying is that you want to pull a base image from Docker and then build on top of that from Docker Hub. And then it says from, this is the base container that you want. And you want that container to be the latest version of the Ubuntu Linux OS, whatever that is. I could stop there and Singularity build this container, and it would give me a blank slate of of a container with a stock Ubuntu operating system on it, period. So that could be kind of nice if you wanted to just interactively build a container on your laptop and you just wanted it to be a blank slate, you could do that. Then you get into the additional things that you need to have in there. Sections below this are all prefaced with a percent symbol. So percent labels is just metadata for the container. So you don't even have to have this section if you don't want it, but it's good in terms of documentation. You can get your name in there. You know, I built this container. I built it on this date. This is version X point Y of the container and so forth under labels. The environment, percent environment, is if you want to have permanently set environment variables in your container, which can be useful, you can set them here. So in this example here, I set an environment variable called hello base, and it's the code directory that I created in my container. The next section you can have is run script. This is also optional. So percent run script. This is where you might put create like a bash script that runs a pipeline out of it. This would be the default behavior you want the user to have, if in fact you want them to have a default behavior, if they type Singularity run container name. And then the last section, and this is really the most important section. This is where everything happens. The percent post section. This is where you're going to put all of your commands to install libraries and software and anything else. So, for example, here I made a directory called code. It's Ubuntu. For those of you who have used Ubuntu, apt-get is the package manager for Ubuntu. So I did apt-get install vim. Vi is a text editor. So I just wanted to install a text editor. And then I created a script called hello.sh. So this would be kind of where all of your work is done under the percent post. So if you had no other section in a typical container, you'd probably have those first two lines, the bootstrap and from lines, and then a post section. Questions? And this is it. So this is what, when you build a container, this is the file you specify to the build command that you want to be built. And then Singularity will go through and build a container based on that. In terms of file formats, the file format that a final container is going to be in is a compressed format that's called squashfs. The actual format that Singularity calls it is .cif, Singularity Image Format. They've kind of customized squashfs for their containers. But it's a compressed format. You can't modify that format. There's another, if you're interactively developing a container and you actually do want the container to be modified as you're building it, you can create an ext, what's called a sandbox, which is an ext3 file system. So that would be kind of like a standard Linux file system. It's uncompressed. So it's going to be a little bit bigger file size. And I'll show you how to do that in the next thing. And then the sandbox, I think, is an ext3 file system within a directory. Okay. So remember, we had the three methods to build a container. Method one, which we're not going to cover today, but I wanted to show you how to do, is this would be from your laptop or from your desktop where you've already installed Singularity. You want to create a sandbox. You don't even know what you want in this container yet, but you know that you want it to have the Alpine Linux operating system. So Alpine is a super lightweight Linux operating system. So it's if you want a really small container footprint, you can start with Alpine and move and kind of go from there. So I could type sudo, because I'm on my laptop, I have root access. Sudo singularity build -- sandbox, and then whatever I want the sandbox name to be. In this case, I'm calling it my test. And then I'm going to I'm going to bootstrap a Docker Alpine kind of image as my blank slate. And then I could shell into that container, sudo singularity shell. And I'm going to tell it that I want to be able to write inside this container. I actually want to modify this container interactively. So I'm going to put this -- writable flag and then the container name. Now you just do stuff in the container from there. And so you can apt-get install things. You can use Git. You can install Git in the container and then Git clone some software repository that you have or that you want to use, and then compile that after you've installed whatever compilers you want in the container, so on and so forth. And you're kind of recording what you want to do from that. So you're going to want to, as you get things right, so you're kind of iteratively doing this, so you have to install the wrong package or you munge up the command. You don't want that in your recipe file. That'll crash the build, the recipe. But so what you're going to do is kind of interactively develop this. When you get the commands right for things that you're installing in the container, you'll paste those into your recipe file. So you're kind of manually creating a recipe file as you do this. You don't have to do that, I should say. What I'm saying is that as a best practice, when you interactively develop a container, you're probably going to want to remember that information at some point in the future so that you can build this container again if something doesn't work right in it or if you need to upgrade it. And so by kind of building that recipe file on the side, you're creating a permanent record of what you did for after you forget what you did. So that's it. So you've interactively developed this container. Now you want to actually use it as a container. There's two ways you can do it. You can just take that writable sandbox called mytest, and you can type sudo singularity build mytest.sif. So you're going to create a container called mytest.sif that's in this compressed immutable format that's portable from mytest. The other way you can do it is that you say you've created your recipe in a file that you called Singularity. So you actually have a file called Singularity, contains the recipe. Sudo singularity build mytest.sif from Singularity. So there's two ways you can build that container to make it kind of a permanent, immutable, portable container after you've done the sandbox. Any questions on that? Interactively. So this is the, if I go back up here, there are three ways to build a container. What I just showed you here was number one, how to build it interactively. And now we're going to do number two. Mm-hmm.
Where does that actually live?
Yeah, just in a you can keep them anywhere you want, but I will show you here. That's a good question. So I have my own GitHub account, and I had you all create one, and I have all sorts of repositories in here, right? But for this course yesterday, I created a repo called Hello OpenMPI Teton. And then at the end of the last session, right before the break, you'll recall that you pulled down a container from Singularity Hub called Hello OpenMPI Teton. What I did was I created a repo. So if you look here at my GitHub repo called Hello MPI.Teton, what I have in there is just essentially a README file that says Hello MPI Teton. You could put some metadata in there about what's in there. But Singularity is the name of a file. That's the recipe I have in here. This is the recipe for the MPI container you just ran before the break. So what I did was I stored my recipe on GitHub in a unique repository. And then what I did, and what we're going to do as example 2 here right after this, is I logged on to Singularity Hub using my GitHub credentials. And then I specified that I wanted to build this container called Hello MPI Teton, and it built it for me on Singularity Hub. And then that was available for all of you and me today in the first session. We did a Singularity poll, shub, : Monahan, hello, OpenMPI, Teton. I know it's a bit confusing. Yeah, and you could call that something else. You could call it like my recipe.def. The reason I named it Singularity here is because when you're remote building, it looks for a file called Singularity. And that's the only reason. So if you're just building on your laptop, you can call it anything you want. If you're going to build from GitHub, call it Singularity. I think it can be. And I haven't, I think you can have different versions of it. I don't know off the top of my head how to do that, but it's in the Singularity documentation. But I've seen that people have done that so that you can have multiple versions of your, a given container. So that if you like keep updating it, you can have other versions. I just have not done that. Okay. So hopefully that was, I just wanted to, this slide essentially, I would normally show you this, but because I'm not on my laptop and I don't have the ability to sudo build a container for you in front of you as a demo, I'm just running through these. So this would be how you do this on your laptop if you wanted to interactively build a container. You don't have to do that, and I would say 90% of the time, you might be able to just use a recipe to build a container on one of the hubs, or download someone else's container who's already built the same thing that you want to run. So then what we're going to do right now is build a container on Singularity Hub using these basic steps. So we're going to create a recipe file for our container. And I've already created this for you in the GitHub repo that you downloaded before the break. We're going to name it Singularity. We're going to create a GitHub repository for the container on GitHub. And I've got a little script that does that for you. And you're going to upload the file called Singularity to your GitHub repository. You're then going to log into Singularity Hub using your GitHub username and password. You're going to go to My Collections and choose Add a Collection. We're going to go through these steps. You're going to select the GitHub repo that you just created and uploaded the Singularity file to. And the container is going to automatically build. And then you're good to go. Then you have a container up on Singularity Hub that you can Singularity pull from anywhere, like Teton, and run. Okay. Is everyone still logged in? All right, that's great. So let's shrink my thing down a hair here. Oops. Okay, so I had the login steps again just in case we got kicked off the machine during the break, but it sounds like everyone's on. Is that correct? Okay. And right now, if you type pwd, you're probably in this run Singularity basic. What you can do is cd down. So now we're just in the base GitHub repo UYO 2019. I want you to cd to build container on shub. And just like the last one, if you need to cut and paste anything, the tutorialsteps.txt file has what you need in it. Let's look. So what else we have in here is we have a script called make-git-repo.sh. This is just a script that I built to make it faster for you to create a GitHub repository with this stuff in it. So we're going to run that in a moment. We have a Python script in here. This is a Python script that we're actually going to put inside the container. And then we have a file called Singularity. Let's open that file called Singularity If you have a favorite editor, you can use that. If you're not familiar with Linux editors, you can use Nano, Singularity. Nano is a fairly intuitive text editor in Linux. And so you can see that we have a recipe for the container that we're all going to build. And so it's going to bootstrap an Ubuntu image. I'm the maintainer. I have some environment variables that I want. Codedir. My codedir is going to be /opt. /opt is typically kind of a catch-all directory on Linux systems, so it's usually safe to throw things in there. Just a text identifier. Good question, yeah. Just metadata that's general that goes in the container. The %file section will copy in any external files. So this can be useful if you have some, in this case, I have a Python script that I actually want to be inside the container. So I'm going to copy texttranslate.py into the OPT directory in the container. You can put other files in there as well. And then we have the post section. Remember, this is the section where you're kind of doing things. And so I have apt-get update. This is kind of the first step you always do when you install a new Linux, when you're installing anything with a package manager in Linux. So apt-get, by the way, is for Ubuntu, that's the package manager. If you use Debian or CentOS, I think it's Yum. At least CentOS is Yum. We're going to install an editor, a couple of editors, VI and Nano. I think we actually don't need this. I just wanted you to see kind of what, you can install just about anything with apt-get. And then we're going to install Python. So we're going to install Python development version. We're going to install pip, which is the Python package installer, and then some other tools. And then what we're going to be doing in our example, this Python script called texttranslate.py, it translates languages from one language to another. So you can give it a string like hello, and it'll translate it to French or any other language. And in order to use that, we need a Python package called translate. So we're going to pip install translate. And then we're going to have a default behavior for our users. When they run the image using Singularity run, it's actually going to run Python texttranslate.py. So it's going to run that script, which is stored in OPT. And then you can also, if you want, as an option, put in a help section. So you can say, so I put in some help text here that if someone types Singularity help container name, it would actually dump this to the screen. So in this case, my help text says, if you just want to run the example script, type Singularity run in the image name. If you want to run your own external script, you can type Singularity exec image name Python and then your script name. So it tells you both ways to run Python. And this tells you how to sanity check which version of Python you're running and whether you're in the container or outside. So that's all this file is. You could change the name if you want. You can make it your name if you want the container to be you. You can change anything in here you want. So I could say, whoops. For example, I could say date 2019 08 09. Okay. And then to get out of Nano, you can type Control X to exit. And then it'll ask you if you want to save the changes, type Y. And then what the file name is, file name to write Singularity, just type enter. Okay. So now we're ready to upload this container. We've done this step, so we nanoed Singularity. We want to be able to run this shell script as an executable. We need to really quick, for some reason, when downloading from GitHub, or when I uploaded this to GitHub, the permissions were lost. And I'm sure that's my fault, but you type chmod +x, and then the name of that script called make git repo. That's going to make it an executable. Now you can see that there's X's in the permissions for make git repo, and it changed colors to be green, indicating that it is an executable. Everyone good on that? All right. So now what I want you to do is I want you to type the script name and your GitHub username. So you've signed up for a GitHub account either previously or today, and you have a GitHub username. Not your email address, not your full email address, but the actual username. So mine is, for example, makeGitRepo.sh, and it's Monahan. It's my last name cut with the last letter cut off. And then I'm going to hit enter for that. Go ahead and do that. I'm going to do something special for me because I've already created this. I won't be able to I have to rename my directory here. You don't have to do that. It's going to ask you for your GitHub password twice. And just enter it both times. And it might throw some warning messages, but you should be good. All right. So I just created a GitHub repo called build container on shub. Yours is going to be called build container on shub. Mine is build container on shub 2 because I already had created a repo yesterday called build container on shub. So if you want, you can go and check and make sure that this thing exists. So if I go to my GitHub account, so go to github.com, Monahan. You can go to yours. You may have to log in. So this is via the web. I can see that I created a repository called build container on shub 2. And in it, it has, as you can see, it has the Singularity file, has the text translate file. It also uploaded this other stuff that I don't need, but I'm not particularly concerned with that. I mainly wanted you to be able to rapidly get this up there. Any questions on that? Did you find it on GitHub? So your repo successfully uploaded? You had some issues? Okay, let's see what we have here. Usually it's a password issue. Okay, let's see what happens. Okay, go ahead and enter your. Okay. No, you're good. Type your password again. Okay, cool. You're good to go. Oh wait, let's log on to your. Can you go to your GitHub account?
I already have one because I was near.
Ah,
Yeah, that's the reason why.
Yeah,
cool.
So how do you? What is it? Just name
You can
it
just keep it on. I mean, you can
it's
just
the
use
same one?
that.
Okay.
Yeah, it's the same one, so
Okay.
you're fine. Yeah, that I always forget that too. I build these for tutorials, and then you yeah. Anyways, you could update it, but the script isn't set up to do that. So okay, any questions online? I'll check. All right. Cool. Okay, so now we know we have this. Okay, so does everybody kind of see where this is going? We're so you've just confirmed by going to your internet browser and getting in your GitHub account that you now have this directory, this repository in your GitHub account. So now what we're going to do is go to singularityhub.org. So I'll do this in a blank browser. So if I go to singularity-hub.org, there we go. All right. And I'm going to log out and then log back in so that you can see this from scratch. So if you go to log in, it's going to give you two options. You're going to do the GitHub, the public. I actually don't know. I've not tried it before. Okay. Okay. So you could get to your private repos. I know that if you're building containers on here, you can build a maximum of like 1 or 2 private images on here. They require most things to be public. So I think if you're not, if you don't have any issues with other people being able to search your containers and use them, then I would recommend just using public. Okay, so you're logged in now. It says some stuff about Singularity Hub. I have my username. What I'm going to do is go to My Collections. And then you'll see a tab for Add a Collection. So let's go to Add a Collection. And yours should be pretty simple. Mine has a bunch of junk on it, but I'm going to choose Build Container on Shub 2. You're going to choose Build Container on Shub. I am choosing the second one because I've already built in a previous session the Build Container on Shub. Sure, go up to your user. So if you go up to this tab, you go to My Collections, and go to Add a Collection, and then it's going to show you your repos on here, and you're going to checkbox the one that you want to build, and that's going to be one that has a Singularity recipe in it. And then if you scroll down to the bottom, there's a Submit button. You can hit Submit. And this thing will start building in a few minutes. Yeah, you can hit refresh there. You can also hit refresh on this. All right. Has anyone entered the queue yet? Okay. And that's what I'm getting to. I think if I remember last night, it took it a few minutes to make things happen here. Let's check. Okay. Yeah, I think. And then I wanted to show you, this is, Tim, this may be new to you. Maybe this is old. I don't think they had this last month, but Singularity had a major change when it went to version 3.x from version 2.x. And so you can build containers in both ways. It doesn't really matter for this example which one you build in. You're probably typically these days going to want to use 3 and set that. You can save that as your default for this container. So let's see where we are here. Yeah, I built last night, but I built it on my laptop. But it did have some of these errors.
Yeah, so one of the things that it's in the notes somewhere, and I didn't see it for several hours. If you had a www.whatever for your link back to your GitHub, that would take that www off.
Okay.
But if it worked for you last night, then you were probably okay.
Yeah, I'm waiting to see what happens here. Does anyone show it in the queue yet? You'll get a button on here that'll say waiting or running. Okay, yours is good. So you'll get some. Okay, good, great. So running, and this will take a while. I just want to make sure you all get to this point to where it's either waiting or running. So there's like a button. on there. And once we're there, we're just going to move on and down. We're going to, it will build if it makes it to that phase. Anyone make it to there yet? Tim, are you might not be doing this.
I'm not, I can do an update on mine and see what happens.
I'll try.
Is building on the Singularity have issues of like
I've seen, yeah, I've seen them. Sometimes they'll blacklist IP addresses if you have a bunch of folks coming in because they think it's an attack. So it's possible that's happened, but I'm hoping that given this early success here, unless this was the first one in, but you know, it shouldn't be. It's a Google runs the cloud service that they're using here, so it shouldn't be too limited. I think you'll see time limits of about an hour for these. So if you have some really huge containers can take over an hour to build, and those will time out. Those ones you're probably going to have to build on your laptop. All right. It's done. It's just a strange thing. I wonder if I can manually.
if I wanted to walk away, I log out and then skin it through and I come back.
Yeah, that's typically what you'll do is you'll submit here. No, no, you can come back to it. Ah, nice. Okay, so it's now queued. Oh, great. Okay, so the way I did that, everyone, if you didn't do that, is I went to settings and choose a manual trigger and then saved that. And then when I went back, it had a trigger build button that it added. And you can select trigger build. It's interesting. Yeah, I guess maybe it's waiting for a new commit. It should have triggered it at the first add. But you can. I think it's looking for the name in the GitHub repo, so I would use Singularity. Yeah. Yeah, so this would be where you could have different versions of the Singularity file that you had mentioned, that you had asked about previously. Okay, so we're in the interest of time, since we have 15 minutes or less left, less than 15 minutes, let's go. I go back to the slides here, and we're just gonna. We're going to pull my container since I've already done this. So if yours is done, you can certainly do this, but um, obviously this is not what you would typically name a container, but it takes on the name of the repository, right? So you want to consider that when you name your repositories. So sorry. So I've already built this container. So instead of waiting for yours to build, since we want to move on, we'll just pull, everyone can pull my container. So Singularity pull, you can name this whatever you want. I'm naming it my translator.sif since this is a Python translation program we want to run. And then Singularity hub Monahan build container on Shub. Okay. Now you'll see that we have a container in our directory, if you do ls, called mytranslator.sif. And I can Singularity run mytranslator.sif. And it translated a piece of code. It translated the string good morning to German, from English to German, Guten Morgen. And you can see that if you remember when we put this script in the container. So this is actually the default run behavior is to run a version of the script in the container. But say I wanted to change the language. I can take that script that I have on Teton outside of the container. So we happen to have that same script in this directory, right? Because this is the script that we stuck in the container. So let's modify this to translate it to some other language you pick. I'm going to do French. You can change the string if you want. So if I try to do Singularity run mytranslator.sif, it still translates this to German. Why is that? It's because it's running the version of the script that I stuck in the container. I want to run the version outside of the container, but I want to use the Python that's inside the container because it has the translate package that I need to run this. So if you remember, instead of Singularity run, which is the default behavior, let's use Singularity exec mytranslator.sif, and then we'll run the Python in the container on mytranslator.sif. And of course, sorry, text translate.py. And it did it in French, which is what I wanted. So that shows you how you can use the software in the container to run. Typically, you're going to have data or scripts or other things on the outside, but you can also have them on the inside if you want. You don't typically want to put large data sets in a container because it just makes them too large. But scripts and stuff like that, it doesn't hurt. Does everybody understand that idea of kind of using software to run things either in or out? I just wanted you to have a sense for that. Let's see. Let's see what you have going on here. Let's see. It is. Okay, let's nano space text translate.py. All right, change your language to whatever you want. There you go. No worries. Okay. In that particular script, is it case sensitive? I actually don't know. So does this need to be capital F for French? Let's see. No. All right. The last and final thing I wanted to quickly do, and I was going to do a demo of this, but and I'll show you how to do this. So you have another option to do remote builds with the Scilab's remote builder. So Scilabs, again, is the company that now owns Singularity. And Scilabs has a container library. That's, if you wanted to pull a container out of it, you'd use the library prefix instead of Docker or Shub. But you can actually create containers with a remote builder on here. And this is super easy. You need to sign in, and you can sign in with your GitHub account. And I was already signed in to GitHub on this browser, so it automatically signed me in. And you can actually cut and paste a recipe in here if you want. The challenge you would have with the particular recipe that we just used was that we wanted to copy a file into the container, that text translate.py script. It wouldn't be able to find it with the cut and paste thing. So you could instead build a container from the command line on Teton. And the first thing you do is you get a token. This is essentially, think of it as a password. So we're going to make one Andy token 2. You don't have to do this, by the way. You can just watch and enjoy. It may not be enjoyable. But I'm gonna essentially copy this token to the clipboard. And then I am going to go on to Shub, and I'm going to create a file. I already have in your home directory, upon the first time you run Singularity, it's going to create a directory in your home directory, a hidden directory called Singularity. We're going to create a file in there called Scilabs token. And I'm going to paste my token into there. Up, of course. Let's go back to Scilabs. Copy token to clipboard. Just make sure here. Okay. Okay. All right, so I now have the token on the system. So this will allow me access to their builder. And I could build a container from here. So I'm just going to quickly call it like test container. All right, so I have the same directory, but I don't have a CIF file in it. So I still have the same Singularity file, text translate. All I'm going to do now is run the remote builder using the command Singularity remote. Singularity build. The remote flag is the key here. And then I can have whatever I want to name this. I'm going to call it my translator.cif. So this is the image name that I want to appear. And then I'm going to call the recipe file is Singularity in this case. It could be named whatever. And it is now building this container on Singularity Hub. And that's right. And you can see that there's a limitation here. It's unable to copy the text translate.py, so it failed. So I'm just going to get rid of that. And I'm going to get rid of that. And now I'm reinitiating the build. And this time, I'm not copying any files in. So there's a limitation that I didn't know existed here, and that's that if you have files you want to put into the container, this remote builder doesn't have a straightforward way to do it. So they either don't have a way to do it, or there's some extra flag that I need that I don't know off the top of my head. Anyways, this is going to build the container. I think I'm going to call it good there. We're at noon. There's a few slides on troubleshooting. If you have the interest, you can go through those on your own. Some caveats. We have some best practices slides for running containers, and then ways of moving containers. Sometimes they can get pretty big. You have Globus for this system. I think that's the easiest way to do it. And then we have some links here as well. And this has been a subject of discussion, believe it or not. I think particularly as I think you'll see more and more containers being used when you're, in the publication of peer-reviewed literature. And I think there's, I would say if it's a small data set, a lot of times it'll be like survey data that might be, if it's anonymized, it might only be 50 megabytes or something. I would say if it's in, less than maybe 50 to 100 megabytes, it's probably fine to put it in the container. If you're going to be beyond that, you're better off publishing, to a repository like, some trusted repository like Open Science Framework, or maybe the University of Wyoming. I'm sure Wyoming has a trusted repository. So I would publish it somewhere where you can get a digital object identifier for the data set, and then have that like in the help documentation for the container. So the container has got the software, but then, with the documentation that's inside the container that you get when you type Singularity-help or Docker help, it's going to tell you the DOI for that data set. That's, I think, would be a best practice. The other thing that does is that the data set's only in one place in that case. And so if somebody just wants the data and they don't really care about your container with software in it, then they can just download the data and they don't have to deal with the container. So.
Our library was working with CSU's library to develop what's called Mountain Scholar is the name of the website. However, I think they kind of stalled or whatever. But to get a DOI from here, at the moment, everybody's emails me and I publish. Yeah, but they usually come in. Because it's hosted on the Peta library through a Ceph cluster, so it's S3 downloadable.
I'm just hesitant to use some of these more local things because I want my data to be discoverable by legal ones.
Yeah. So we publish all the metadata from our DOI stuff.
You can do these after lunch if you want to. Yeah, these can be done anytime, and I'll put an envelope up here. Sorry.
We'll come back at 1 Mountain Time so that we all get lunch, and we'll start up with Tim on Parallel R.
Okay, everyone on Zoom, lunch till 1 p.m. If you want to fill out this survey that's in the thank you slide at some point today, would greatly appreciate your feedback on this lecture.
So welcome back. I think I need to turn something down here. I'm hearing myself, and that could cause problems. Oh, okay. Well, I thought that did it.
Where's the here? Where's Zoom at? Go to audio settings there. The arrow next to unmute.
Oops.
And then speakers, audio settings down here at the bottom.
Okay.
And then output level turn to 0.
Okay.
There you go.
Good. So, as I said, welcome back. And this afternoon, we are going to be talking about R and doing R in parallel. So, a couple things, and I want to thank our last speaker for suggesting this. He maybe didn't realize he suggested it, but that URL at the top there is kind of long, and so I actually put in a small one, a tiny one. That I don't know how long this is going to work. I've never used this particular service before, but it worked as of a few minutes ago. So the slides are available off of that webpage, and there's a bunch of other stuff. The slides and the source and everything is available there. So you'll probably want to open up a browser to look at that. So you got some claims and disclaimers. Number one, I am not an expert in R. I don't use R. The only time I ever do anything with R is when I'm helping other people. I am considered an expert in parallel programming. I've been doing it longer than some of the people in this room or have been alive. I have developed a number of parallel packages in many different languages, including Python, C, C++, and Fortran, and a few other things that people have never ever heard of. I am not an expert in earthquake simulation. I have done it, and you'll see how that comes into play here in a few minutes. I do have a couple of publications that I wrote with a student back when I was at Mines. In particular, he walked into my office one day and he said, I have this application written in R. I want to use your supercomputer so that it will run fast. And I told him it ain't going to happen. And I told him that that particular application needed to be written in a compiled language. He left my office, came back a month or so later, had taught himself C++, had the application rewritten. At that point, we parallelized it, and he actually graduated, as opposed to maybe he wouldn't have. And another thing related to that, as I said, I'm an expert in parallel computing. The people that have developed the packages for doing R in parallel are R programmers. And you can read into that what you want. And bottom line, I am not convinced this is a really good idea. And you'll see why, because there are things that just, you kind of scratch your head using these various packages that we're talking about. They just don't seem to work the way you think they should work. All right, so there's actually two paths that we're going to try and cover today. And there's a package called Parallel in R. And if you are familiar with OpenMP, it's sort of like OpenMP, except it does not launch threads. It actually launches tasks, which has some advantages and disadvantages. We will also be talking about a package called RMPI. In the last talk, MPI was mentioned, and RMPI is a version of MPI that is built to work with R. So I have far too much material to cover. My hope is, I can get you looking at this stuff, and then you can go back and say, oh, well, let's go down this path. You basically have three separate presentations that, like I said, we're just not going to get through all three of these today, unless I talk a whole lot faster. So with the RMPI, we're going to look at some simple examples. An odd example, and it turns out this is one of those things that will work on some platforms. It turns out it does not work on the platform here, and I am not surprised. And I'll explain a little bit why that doesn't work here. And we have 3 full examples. Finite difference code, it's called the STUML code. That's the application that I normally use when I teach parallel programming. That's sort of my typical example. In bag of tasks, I think this is probably the best use of R that we are going to hit today, this whole bag of tasks, parallelism. And it actually highlights some things that really would potentially work well in R. And then the final thing is, and we're not necessarily going to cover these in this order, we're kind of intermixing them. We're actually going to do a earthquake hazard map for Southern California. When I was asked to do this talk, I was told, well, do something geospatial. And so I was scratching my head for a while, and geospatial's, earthquakes sort of geospatial. And briefly cover what I would call the normal parallel R, and that is not MPI based. That is with this package called Parallel. There's a library Parallel, dplyr, and library do Parallel. And there's this other one that we're not going to talk about today because it's still under active development. And it turns out that like a week or 2 ago, I had all my examples together and up and running. The guy that wrote this package did some updates, broke half my examples. So I just tossed it out. Let's see, some other things that are not, yes. Pardon? Future? No, haven't used it. Okay. Okay. Here. Please, I don't want to be here. So these are some things sort of outside of R, but are actually applicable to the kind of stuff that we're going to be looking at. Forcing tasks to cores. There's actually in this parallel package there is a routine that in theory will force tasks to cores. But the way I'm going to show you how to do it, it's portable. Some monitoring tasks, splitting files, and writing files as binary. Okay. So just a bunch of lists of references, and again, I scratched that one for now because that's the package that did not properly work for us. So you can actually get the stuff. If you go to that link, the tiny link, and you will see in that web page, you'll actually see a whole list of files. What we want is the pr.tgz file. So here's what I'd like for you to do. You can do this if some of the stuff we're going to be running with RMPI, not RMPI, with RStudio, and that will work on these machines. Some of the stuff that we're going to be running, and they're actually fairly short. You can decide if you want to do it or not. But some of the other examples we're going to run on the cluster. So if you want to run on both, you're going to have to do this twice. So make a directory. I just called it toot. CD into that directory, and then curl that file. I would recommend that you click on the link from that web page and copy paste. Oh, the original one? Sure. I'm not guaranteeing that's going to work. If it doesn't, sorry. Yeah. Okay, good. Yeah, so the R stuff PDF are the slides I'm looking at. We're looking at right now. Actually, why don't I go ahead and pull up that page? Yeah, the slides, there's 3 sets of PDF files, and the ones we're looking at right now are rstuff.pdf. Okay, and this is the link that has a tarball of all of the files. So what you can do, I'll just make a new directory on my machine here. Oops, wrong machine. Yeah, this is small stuff. I mean, it's actually one of the data file starts to get a little bigger. And the other option for getting this is that you can if you've downloaded the HTML, I'm sorry, the PDF, you should actually be able to copy paste this link from the PDF. That's probably the easiest thing to do. Yeah. So yeah, so if you copy from the PDF, you can copy paste this whole line, everything that's in red. I'm a firm believer in copy paste for getting things to work right. So once you do that, you should have a directory called just R. And then inside of that, there is a script. We're actually going to be working with two data sets. And this get pi, which I should have written in R, sorry I didn't, it actually downloads a fairly good size data set, 630,000 earthquakes from Southern California for the last however many years. And it does some things to it and splits it in a set of files. And then the second data set, just source this file zap. Oh, I just got a question. Where is the link again? All right, so let's go back to that. Whoops, need to stop that. Okay. Okay. Pardon? Oh. Okay, so again, this will give you all the source, and then these two lines. This line here will get the earthquake data set, and this is actually going to get another data set that's actually some optics, output from an optic program. And this is what you'd get. Actually, I've actually added a few files since then. So you'll get this plus like 2 or 3 more files. That's what you should have in your directory. And lots of stuff there. And we're not gonna, don't worry about it. We're not gonna go over all of that. The one of those that's probably you will want to look at, there's a README file. I don't even think it's listed on here. There's actually a README file in here that basically explains what all the other files in the directory are. So you might want to take a look at that. In fact, let's go. This is, again, just a list of the README files actually at the top of that web page. It just lists every a short description of all the programs that are in this directory. The names are not very descriptive. Sorry about that. They mean something to me, but that's something I think I need to change the name of these names of these files so they actually mean something to people that aren't me. All right, so parallel programming, basic MPI. So we're going to start with that. and then we're going to talk about the parallel package, and then we're going to show how you can mix them, and then we'll get into our hardcore earthquake simulation example. So a little bit of overview. We talked a little bit about MPI in the last session, but I want to give you a little bit of background on it, tell you where some of the documentation is. I'll show you some hello world type examples, talk about the differences between our MPI and normal MPI. We'll look at some basic communications, simple send and receive programs. And the thing that does not work on your local machine is spawning. And what a spawn is, it actually, you start an MPI process, and then you get that MPI process to start additional processes. And like I'll talk a little bit more about that, but it works some places, it doesn't work other places. I was surprised to find out that it actually does work on Summit. But the place I was at before, CSU, it did not work, and it apparently doesn't work here either. It all has to do with how your scheduler is installed. You know, if you set this flag when you install the scheduler, it will work. But I don't think that's something we need to worry about, because I actually think there are better ways to run things that you would normally do with spawn, and I will talk about that. So MPI, as was mentioned before, MPI stands for Message Passing Interface. It's a library standard defined by a bunch of vendors, parallel programmers. It's not something that's new. I mean, it's been around for well over 20 years. And the first standard came out in the the late 1990s. And it's used to create parallel programs based on message passing. So it's a standard, but there are many implementations. And also, as was said earlier, it's available on any parallel machine that you're going to see that does high performance computing. The officially supported languages are C and Fortran. There are also a couple implementations in Python. I actually wrote one of them. The one that is normally used is PyMPI, and I would recommend that one over the one I wrote, because it is much more complete. R is not one of the officially supported languages. There are, it says here 100 100 routines in MPI. That's probably actually closer to 200. There was 123 in the initial standard, version 1. I think we're now up to, we're closing in on version 4. So they've added lots of routines. But you can do most things with 6 basic routines. And those are the ones we're going to talk about most today. The other thing I want to mention, RMPI is a very small subset. You can actually do things. There's actually a few calls that are extensions to the standard version of MPI, and we'll talk a little bit about those also. So documentation, this is the link for the RMPI implementation, but if you're just looking for tutorials on regular MPI, just go online and do a search. You'll find some. You might actually find some really old ones dating back to some videos of me doing a presentation at, I think, the University of Michigan. So there are actually a couple of books that are available online, and these 2 are actually old, but they will get you started, and they are free. In that they were originally copyrighted, but they now have been released to the public. So MPI implementations, this one was mentioned earlier, last session, OpenMPI. It is one of the more common ones. Intel actually has their own implementation of MPI. I actually kind of switch between these 2 depending on what I'm doing. As with any package, there are things that work better in one package than in the other. And there are actually some applications that flat out will not work in one implementation, but they will work in the other, which that's not supposed to happen, but it does. Let's see. And these are two other implementations of MPI. So the key concepts. Again, some of this was mentioned this morning. It's used to create parallel programs based on message passing. Normally, this is not a requirement, but normally you have the same program running on all of your processors. And the processors communicate by passing messages back and forth. So the way this works is that your typical methodology is that you will start a job on some number of processors, okay? And then you're in some kind of loop. And in this loop, what you're doing is the processor will do a calculation, and then you'll pass messages. Calculation, pass messages. Obviously, there's different stages of the calculation. Things can get a whole lot more complicated, but this is the basic structure of an MPI program. That's how they work. So messages. So messages are essentially, they're arrays of data, okay? And if you're sending a single value, then, well, it's an array of one element. So in Fortran, there's a real type corresponding to a float in C. There's a double precision in Fortran, a double in C. There's an integer in Fortran, and also an int. I'm sorry, I don't know why. Oh, yeah, there's MPI int in C. And the user can define data types based on these. You can have structures that are some number of integers, some number of reals, et cetera, et cetera. R is a little different. R, instead of having names for these data types, they're just an integer. So a data type of 1 in your communication is an integer. Data type of 2 is a double, and you can have character as 3. And R adds another data type, and I'm coming more from the Python world, so please, someone tell me what this is actually called in R. In Python, you would call it a pickled data set, which is basically a structure that's compacted together that you could actually save to a file. Is there a name for such a thing in R? Okay, well, then you would save it, yeah. The bottom line is that in R, you have lists, you have data arrays and whatever, and you can actually send those as an entity in R. The Python, yeah, class, and Python actually, the Python implementation of MPI has the same capability. So you don't have, if you have this bizarre data structure, you can actually send it as a complete, just one package, and it'll get to where it goes, and then R on the other end will actually know how to unpack it. Okay, a communicator. A communicator is a collection of processors that are working on some type or some part of your parallel job. It is a parameter in 90+% of all MPI calls. There is this thing called MPI COM world, which is sort of the default communicator, although it isn't in R for some reason, I don't understand. And this includes all of the processors in your job. It is just basically, it's a set of processors. Okay, they are given a number, 0 to n-1, and yes, that is 0 to n-1, even in Fortran, even in R. This goes back to C convention, where you typically number things from 0, but in R and Fortran, you typically number things from 0, from 1. You can create subsets of MPI COM world. And this is actually one of the things that's sort of supported in R, but not in the normal way. And we'll look at that a little bit. All right. Okay, so when you are building a program with MPI, in Fortran and C, you have include files, MPI.h or MPI.f.h for Fortran and C. These define a bunch of variables that you need in your programs. In C, they actually define the interfaces for the routines that you're going to be called. There is not really an equivalent, but there sort of is in R, in that whenever you load this library, it also gives you all of these variables that are normally defined in the include files. The interesting, well, I'm going to get back to this. There's another interesting thing that happens when you load this library in R. All right, so minimal program in C, you have your include files. And the first thing that you do is you do an initialization, okay? And you do, the last thing that you would do is a finalize. Those are technically the only two calls that you actually have to have in an MPI program. Without those two calls, it is not an MPI program. It will not work. All right. The other two that 99.9% of every MPI program are going to have, they will have a com size and a com rank. What com size returns is the number of processors that are running in your parallel job, and com rank is that number in 0 to n-1. Okay, and here's the difference with RMPI. You don't need to call initialize. When you load this library, and just want to point out this stuff right here, this line right here is actually not needed. The only thing you actually need is this library RMPI. Okay. So when you load that library, it actually does the initialization. So then you can get the, you can actually get the ID by calling MPI com rank and the number of processors by calling MPI com size. And here we have specified our communicator as MPI com world. Okay. And again, remember that MPI com world is the collection of all the processors that are in your parallel job. All right, so as I said, MPI programs are based on message passing. So we got the C version, Fortran version, and the R version. So what you are sending is you are sending some data. Okay, that data has some type. You are telling it where to send it. Okay, this is a processor number. Okay, you are giving that data a tag, and you'll see that there on the receive end with MPI receive, there will be a tag there also. In order for a message to be sent from one machine to the other, or from one processor to the other, the tags have to match. If they don't, your message is going to get lost. And you also have to specify the communicator. Oops. I guess it's on a later slide. This is kind of weird. The default communicator, I mean, this is one of those things that actually is default in the call. You don't have to have it. Is actually 1. And I actually think it should be 0 because 0 corresponds to MPI com world. So the calls actually block until the message is on its way. Notice I didn't say blocks until the message is received. Okay. If you send a message, okay, it gets put into some buffer somewhere and gets sent on its way. That does not necessarily mean that the receiving process has yet received that data. Okay, if it doesn't eventually receive the data and things start piling up, you send a bunch of messages, eventually you're going to overfill a buffer and your program's going to stop. You'll get an error message. Okay. This is just, okay, more detailed description. Again, for a data type in R, we have integer, double, or character. And this is the receive. Okay, so again, we have, oops, this is, we have to have a buffer that is defined for the receiving data, which is really weird. And you'll see why here in a few minutes. because basically the way the data is actually given to you, it's actually as return value. Okay, so I'm not exactly sure why you actually need this buffer, but it is required. You have a type. Okay, this is where the message is coming from. As I said, the tags have to match between sending and receiving. A communicator, as I said, I personally think should be defined as a default of 0. And then you have to have a status. Status is actually used for getting information about a message. You can actually get a status information about a message before you receive it. And I'm not sure if I don't think we'll talk about that today, but that's actually useful if you can find out how big a message is before you receive it. And that way you can pre-allocate space for it. So you don't necessarily, you're not going to overrun a buffer. So that's how that's often used. All right, so the, oh, that's interesting. I intend to do that. So on the receive end, this call will actually block until the message is in the buffer. Okay, this is just the receive, this the full-blown explanation. All right, so this is the almost a little bit more than hello world in MPI. Okay, we start out with, we do the initialization. We load by loading the library. Okay, our MPI-COM world is 0. We get our the ID for the individual processors, the number of processors. Okay, and this is another kind of cool call. You actually can get the name of the processor on which you're running. Okay, this is useful in a lot of contexts. For example, if you're running across a bunch of different nodes and for some reason you want to know which node is doing what, you can actually find out. And here, we're just pasting that information. Okay, and now here's where things start to get interesting, in that you have, as I said, you normally have the exact same program running on multiple nodes. But look what we've done. Okay, we have an if statement here. We have source, whoops, source is set to 0. Okay, so if my ID is equal to 0, in other words, if I am the 0th processor, then what I'm going to do, I'm going to put some data in a buffer, and then I'm going to send it. Okay, I'm sending it to processor destination. Okay, and destination is 1. So if my ID equals destination, a pre-allocated buffer, again, I'm not sure exactly why you need to do that, but things don't work right if you don't. And then you actually receive it. And then finally, we print this out. All right, so let's go ahead. I'm going to, I'm not sure it's worth your while to actually be running this stuff, especially the MPI stuff. I mean, when we get to the R Studio, that's a different story. But the R MPI, these things run in like a half a second, except for one. One of the examples takes considerably longer than that. So I'm just going to run these. Oops, escape. I will run them on. I think I need to make that a little bigger and make the window smaller. All right, so this is on a machine back in Fort Collins, and let's see. We'll figure out. Actually, let me pull this up. So our hello world is this one right here. Okay. So get back to my terminal, window. So this is what we just had on the slide here a few minutes ago. So I'm gonna run this first on 2 processors. All right. Another side note here. The way we usually typically launch these parallel or the R MPI applications, we actually use R script. And then the name of the executable. And that's it. We just ran a parallel MPI application in R. So we have our machines semicolon. Okay, we have task 0 of 2, task 1 of 2, and task 1 actually doesn't say task 1 here, but we could put that in there. Task 1 actually got the value back. Okay, so let's just for grins, let's go ahead and run this on 4. Okay, so the only difference here, the only things that actually did, the only processor that actually did anything in this code were 0 that sent something and 1 that received something. So we have that output got is actually from MPI task 1. But the other ones actually just basically said that they were running and they gave the name of the machine on which they're running. And other than that, they were pretty much sitting idle or didn't do anything else. Okay, and so that's the same stuff we saw there. All right, some other calls. Broadcast. Broadcast sends a message from one processor to all of them. The same message goes from a single processor to every processor. This is often used when you initialize an application, when you first start up. You say, here's the process 0 will read in some data, like maybe a directory for where your data is stored. And so you'll send that information to all the other processors so they need to know, or so they will know where their data is. Okay, MPI reduce combines each processor's data into a single value using an operation. And these operations are min, max, sum, product, and there's a few other ones that are more obscure. Gather each member's message to a single value or to a single processor. No, I'm sorry, not a single value. And then MPI gather V. These two are closely related. The difference is for gather V, you're actually, each processor can send a different amount of data. All right, so here's broadcast. Again, here's the data that we're sending, the type. We're broadcasting from 0, our communicator. And this is just another buffering value that I believe it's actually not required. If your messages get very large, they recommend that you increase this buffer size. There's information about that in the documentation. All right, reduction. So we have a data value, again, our type, and then the operation is one of these. So it's sum, product, max, min, and the other two that I didn't mention, max loc and min loc. And what these do is they actually give you a location for the maximum or minimum of the values. And again, the destination and the communicator. Gather. So again, what you end up doing is that every processor calls gather. They put their data in here. Again, you have to have the type. This is where the data is going to, your communicator. And this is a pre-allocated buffer for your data, which again, I think is kind of silly, but oh well. All right, so here is our second application. It actually let's see. Yeah, it doesn't. This one does. I thought it doesn't have gather V. It does have all the other ones that we've talked about. So we start out with we just output again just a info line telling us who's doing what. If you're the source, you fill this buffer. And notice here, I mentioned this, that I actually am pre-allocating that buffer for all processors. So everybody does this line, but only process 0, or the source does this one. Yeah, that would be bcast. Yep. Yeah, again, the names are, I mean, it does more than bcast, but bcast is the first call. And then we have the gather, reduce with an operation of sum and a reduce with a product. We're actually, the reason I have these particular calls is that we're actually going to use them in our earthquake simulation. These in particular, the one that gets used big time is the reduction operation, and you'll see that. That's the most important call in that MPI call in that application. So, well, yeah, let's just go ahead and run this one. Gee, we got exactly what we expected. It's nice when that happens. All right. This actually, I think, is important. You can mix MPI programs. You can mix a C MPI program with a R MPI program, with a Fortran MPI program, with a Python MPI program. I say you can do that carefully because, as I said, R MPI is a subset of full MPI, so you have to use everything that is in the subset. And the other thing that you need to be careful about is I mentioned that you have the integer, real, character data, okay, but you can't send an R. We never did quite decide on what that's called, an R pickled thing to a Fortran or C program and expect it to actually know what is being sent. And I mentioned this also earlier this morning. I do have a container that has everything that we are going to be talking about today. It is in the container, including a version of MPI. The difference between what was mentioned this morning and my version of MPI is that the issue with getting MPI to work on a cluster, as was mentioned, you actually have to have the same version of MPI installed on the cluster that you do in the container. I get around that by essentially sacrificing performance. Okay. And the big performance that you are sacrificing is that the version of MPI that I have in my container will not work across nodes. It'll only work on a single node. Okay. And to get it to work, as I said, to get it to work across multiple nodes, you have to have the same version installed both locally. All right, so we'll start the container. Okay, the next thing is that we have our C version of that program that did the send and receive. Okay, next line, we have the R version. This should look familiar. We saw this a few minutes ago. Okay, then finally, we have R and C mixed together, or we have process 0, okay, is C, and process 1 is R. And this is a little different syntax than you would normally see because we are splitting this. And there's different versions of MPI and different schedulers have different ways of specifying what's called non-heterogeneous MPI. And for this version of MPI that I was running, you actually specify the number of tasks that you want to run in your first set, then a separator, and then the number of tasks that you want to have in your second set. And I haven't done this, but there's no reason why I could not have thrown in Fortran and C and Python. This container actually has Fortran MPI, C MPI, and Python MPI. So you should actually be able to have 4 or however many languages I mentioned, each running basically the same program as completely different languages. So why would you want to do this? Okay, think about what is R good at, what is Python good at, what is Fortran good at, and what is C good at. Okay, what is 2 things that R is noted for? Okay, huh? Visualization. And that's not what I was going to say. Statistics. Okay, statistics and visualization. Okay, what is Fortran and C noted for? Speed. Okay, so what you might want to do, and I don't have it in this talk, but in the Python version of this talk, I actually have a example where I do calculation, hardcore calculation in Fortran or C, and while that calculation is running, I actually have Python doing visualization of the calculation. Okay, that's why you might want to do this. You use the language for what it's good at. Okay. Anyway, okay. Oh, so there's Singularity poll. Yeah. And that's another thing. I need to, everything's there. I'll be making some changes to this because it's not real obvious. As was mentioned this morning, a lot of stuff is, you usually put your stuff in a directory called opt. Well, that's where everything is, but it's kind of scattered around there. It's not really well organized. I really need to modify my container recipe so it's a little bit better organized. And I'll do that. Probably not going to happen next week because I got a bunch of other stuff going on next week, but in the next couple of weeks. Okay, so if you go online and say, show me a R NPI example, it's a good chance this is what you're going to see because this is the first one that I saw when I started searching for R NPI examples. And this is the one that doesn't work on the local machine. Let me explain to you what's going on. Okay, and why it doesn't work. So we start up here, typical we load the library. Okay, and then we do a spawn. Okay, and we're actually spawning tasks. Okay, and this is something that is in the MPI standard. Okay, and when you do this spawn, these actually are MPI tasks. Okay, they are, they're basically, they just get added in a kind of an odd way to your pool of tasks. Okay, so you start out with 1, and then here we are adding 4 more, so you end up with 5. Okay. The issue, and I mentioned this already, but I'll mention it again, is that the scheduler that is on your cluster has to support that, and most don't. It is something that you can add into your scheduler at build time. Most places don't, and there's a good reason why they don't. It's probably not a good idea because what's going to happen is if I ask for say, 2 processors on my node, and you have shared nodes, and somebody else grabs the other 26 processors on that node, and then I try and spawn however many more, well, you're walking on each other. It's just probably just not a good idea. So anyway, all right, so let's just run through this. So we're spawning a bunch of tasks. The stuff in the middle, again, this is part of the original code. It basically, this is what happens if it fails, and I'm sure that when you guys tried to run it here, you saw messages from this block of text. And then what we're doing in this case is nothing. We're just basically saying, okay, just print out your rank, okay? And so it's really not doing anything. I will actually show you in a few minutes when we can actually combine the parallel R with RMPI, where I actually use this and to some pretty substantial performance improvements. It was really kind of cool how it worked. All right, so this is just output from that. As I said, we started out with 1, we added 4, and then each one printed out that they were running, and they quit. So as I mentioned, I think there's a better way to do this, and that's with a bag of tasks. And wow, when are we supposed to take a break? I'm fine just going through this because because like I said, I got tons of stuff, and I'm talking fast enough that I might actually get through this. I do want to talk about this bag of task stuff. It's actually pretty neat. Let's see. Actually, yes, let's go to that now. Okay. So I need to switch. And we'll come back to this. And remember when I said that we want to use a language for what it's good for. And that this is a good example of using parallel R for something that it's good at. So bag of task parallelism. So you have a bunch of things to do. They are all independent. Basically, you have the same stuff that you want to do, but you have a bunch of different input files. This type of parallelism, sometimes called bag of task, or you might hear of somebody talking about something that's embarrassingly parallel, because what you can do is that you can start all these things off. They have absolutely no communication between them, and they just run, full machine, as fast as they can go, because they don't have to wait on each other. They just go. And you typically have a manager that, so you sacrifice one worker to do management, okay? And it basically doles out work. So what happens is that you have, and we'll see this here shortly, the workers say, hey, I'm ready for something to do. Please send me something to do. Manager sends a task, okay? And they do their work and probably read in a file, output a file, and then they come back and ask for something else to do. So one of the things that this is an application I have written in C, Fortran, Python, and R. One of the things I actually use is a split communicator call. That's one of the things that is not supported in RMPI, so I actually had to make some minor changes to this program. It works just as well. It's just different. So we have some number of processors in. In this case, we have one manager, and it is waiting for that message from all the workers saying, hey, I'm ready for data. And then the rest of the processors, they're in a loop, okay? They get data, process the data, send back results, get data, process the data, and send back results. All right, so this is just the source. This is, I think, BOT, I think, on the list. I remember, or it's either BOT or BAG. I don't remember what it's called. Okay. And what we're going to do in this example is we're actually going to do some image processing, sort of. Image processing is maybe an overly glorified term, but we have a bunch of data that is output from an optics program. What the optics program does, it calculates the propagation of a laser through the atmosphere, and this actually turns out to be something that's fairly complex, and huge program to do this, but it outputs data. And what it does is, as the beam propagates through the atmosphere, it actually takes slices. And we'll have 201 of these slices, okay? And so here's the program. Oh, one of the other things that I did not mention, oops. Back. Am I going the right way? Yeah. MPI actually has, stop that. MPI actually has its own timing routine, which basically gives you seconds since some arbitrary time in the past. You are guaranteed that that will not overrun in the time that your program is running. So we do our initialization, okay, set com world, get our ID, number of processors, and again, this isn't important, it's just kind of interesting. So then what we do is that we're actually splitting these up into two groups, group 0 and 1. And as I said, MPI does not support com split, so that's actually taken out. It's technically not needed. For this example, it would have been useful for some other ones, but anyway. All right, so group 0. So there is going to be one processor in this group, and that is the manager, okay? And he's going to call, he or she is going to call a subroutine called manager, okay? And we'll look at that in more detail. And it's going to keep looping in this subroutine until all the work is done, continually sending work to all the workers. Okay. And then print out that it's finished. This barrier command is basically a command. I didn't talk about this, but essentially what it does, it just sits there and waits for all of the other processors to finish their call to barrier. Then we call finalize. So that's what the manager does. Okay. The worker, well, pretty much the same thing, except he or she calls a routine called worker. So, okay. So the manager is going to read a file, in file, okay, and reads it, in this case, as a CSV file. And there's actually no commas in this. It actually is just a list of files. And each one of those files is data, a data file. Okay, and I'm not going to go through this in any detail or a whole lot of detail, just hit some of the highlights. We're in a loop. Okay. Okay, so the manager, another routine I didn't talk about, probe. I did mention this briefly. This is actually how you look at a message before it comes in, okay? And we're actually finding out where the message is coming from. Then we actually receive the message, okay? And that message that is received is actually a message from the worker saying, I'm ready to receive additional work to do. Then we actually send a message to the workers. In this case, it is a name of a file. And then we're just in a tight loop. We are waiting. The probe, actually, in this case, the reason we're using the probe is that actually will also tell us if there is a message that is ready to be received. In addition to telling you what the message is, you can actually set it. You set the flag so that if there's a message that is ready to be received, that returns true. And then you actually go into this block of code and actually receive the message. So the worker, oops, that's still cleanup. Oh, shoot. I didn't actually talk about this one. I should have. This is actually what the worker's doing. I went through this one too quickly. Okay, worker. Actually, you know what? I need to look at the source because I don't. Actually, it looks like there's something missing here. Sorry about that, but I will pull up the source. All right, so this is the routine that actually is the worker. Okay. What we're doing is that we start out, we send a message to the manager saying that we're ready to receive data. We receive a name of a file, okay? And then we actually do something with that file name. In particular, what we're going to do is we're going to read that data and plot it. So here's the do plot routine. Loads a library, creates an output file, and actually reads in the data and plots it. All right, so let's go ahead and run this one. Remember if I need to, yeah, I think that'll do it. Neither. Yeah, this is actually my desktop machine. I've got it to work at least 2 places. So if it doesn't, then we need to, yeah. Yeah, I think I know why. I have a feeling how I screwed up, and I think probably what I. Oh, did you load the library? Okay. Okay. I think probably I didn't set the in the container. Probably didn't set the environmental variable to point to the lib or the directory. Thank you. I will check on that. But my guess is that's exactly what's going on. So anyway, so that happened so fast you don't realize how cool this was. So let me do it again. Okay. I am going to process 200 files. And we're done. Okay. Mornings are highly overrated. So this is actually the reason this is so cool, this ran in roughly 9 seconds, or 10 or so seconds. It would have taken 3 times longer as a serial application. All right, so what did we actually get? So we had, like I said, 201 data files. And they're just basically just a bunch of integers. Okay. Remember this kind of shape you see there. Okay. Well, actually, it does. It does look like a face. There's actually one that, anyway. So what it did was it took those files and it created 201 PNG files in parallel. This is cool. This is how R MPI and how R should be used for in parallel, because this just works. All right, so what I would do next is take your favorite whatever application that takes PNG files and strings them together, and you have a movie. This is a movie of a, has it started? Yeah. Oh, I know why. Yeah. I think I need to go back. Movie of a laser propagating through the atmosphere. Post-processed with R. To me, that's cool. Anyway. Okay, so that's a bag of task parallelism. And the other thing that I mentioned that I do have a full-blown R implementation of is a finite difference code. And if we have time, I will talk about that. The slides are there. One of the reasons I don't really know that it's a good thing to talk about, and I talked about things that languages are good at and things that they aren't good at. This was not a good thing to be doing in R. It is very, very slow compared to compiled languages. We're talking on the order of 1,000 times slower. So anyway, okay, so back to our first presentation. Let's load that one. We can get rid of this one for now. So, parallel R. And in this case, we're going to be talking about a library parallel and a library do parallel. This technically is not a parallel thing, but is very popular and quote adds grammar to R. And I just have, again, these are just screen dumps of some of the documentation. This is for the parallel package. More on the parallel package. And do parallel. More do parallel. And for each, which is part of this whole package or collection of packages. And and we're not talking about that one. All right. So now this stuff should work under RStudio. So if you want to follow along, feel free to. If you don't, I'm going to do most of this stuff in RStudio, and some of the stuff I'm just not going to bother doing because I have it on screen on slides. But so the way this is going to work, need to get out of this. All right, in RStudio, you need to you need to set your working directory to the directory that contains all the examples. So in my case, that's my home directory slash, I think that's what I called it. And I need I'll soon find out if that's correct. Yep, that worked. Okay. So that gets us to the directory. And inside of that directory, there's a file called semantics, and there's a directory called semantics. Okay. The file semantics contains the same stuff. I'm sorry, the directory semantics contains the same stuff as the file semantics. It's just broken up into 14 different individual files. So you can load individually, or what I'm going to do is actually load the whole file at once, and then just selectively run things from that. Just to show you what I mean. So there's, actually, I guess it's actually 16. For some reason, I remember 14. So that's the individual ones. But then I'm going to load this that, like I said, it contains everything that's in that directory. Okay, so the first thing that we need to do is that we actually need to load these libraries. Okay, so in RStudio, we have this whole file there, but we don't have to run the whole thing. We can actually just do this. All right, so what we just did was that we loaded these libraries. The parallel, this one is commented out. I'm not sure if you can see that. We loaded dplyr, parallel, and do parallel. And I actually set this variable to 4 because I'm going to use, for all my examples, I'm going to use 4 tasks. Okay. All right, so that's the first thing. Then we scroll down a little bit. I'm just first just going to do a little simple loop. Okay, this is not in parallel. Let's clear this. Boom. Okay, so it just added a bunch of numbers up and came up with 55. Nothing exciting. All right, we'll scroll down a little bit more. All right, as we noted, we loaded those libraries. We set the number of cores to 4, but we actually haven't started anything. Okay, there are a couple of commands similar to what you would do with MPI, where you do the init, but in the parallel packages, you actually have 2 commands that CT and register do parallel. These 2 commands combined together will allow you to run 4 loops in parallel. Okay, so we will go ahead and run those. All right, so we now have 4 copies, actually 5 copies of R running on this machine. Okay, actually, I should be able to see that. Let me pull up. They're there somewhere. Okay, they're there somewhere. I don't see them with all that. They get cut off, and I don't. Anyway, take my word for it. They're running. Okay, so we now have 4 instances of R running. They are independent in the sense that they are actually independent processes. Okay, the RStudio in some sense, is actually managing these, just like we did with the bag of tasks, where we had one process managing the rest of them. RStudio is managing these things. All right, so let's go ahead and actually do a loop. So here is, can I make this bigger? Yes, that's nice. Okay, so here's our for loop. It has a little bit different syntax than a normal for loop, in that we have this extra thing in there called do par, which basically says do this loop in parallel. Okay, so we remember what the last version of this loop returned. I think it returned 55. Okay. So let's go ahead and run our nice parallel loop. Yes, I can definitely tell. Wow. The machine is, you see how the cursor's kind of jumping around? Okay. What's going on, what's happening is it's actually got those extra R tasks are just sitting there spinning. And this thing only has two cores, so it's way oversubscribed. So that's what's making it, anyway, okay. So we're gonna go ahead, you know what, actually I wanna try one other thing. Let's see if top shows something. Oh, that's just weird. All right, as I said, take my word for it, they're there. Go back to RStudio. All right, we're gonna run this. Okay, we got to put this line in. What happened? Print a sum. 0. No. Okay. I'm going to do a bunch of stuff here in the next couple of runs that basically what I'm going to do is slowly build up to a piece of code that actually works. Okay. And the reason why I'm doing that is basically to show you how things are different and how you actually have to change your original R to actually work with this parallel package. And this is in reality the steps I went through when I was actually teaching myself this stuff. Okay, so this doesn't work. Well, the first thing that we have to note, and we'll see this. Let's see, let's stop this cluster. Because we're going to restart it. Okay, the first thing is that the for, okay, you actually have to explicitly assign the parallel for, you actually assign output. Okay, I'll show you how that works. All right, so we're starting up our cluster again. Now, okay, here, notice that we have the assignment. For each is actually assigned to bsum. Okay. And we are going to print, when we're all done, we will print a sum and bsum. Okay, then we'll stop the cluster again. Okay, we actually got something out that time. 18. Let's do it again. 20. We got 20 again. 23. Oops. All right, so clearly I'm not understanding how this is supposed to work because this is obviously not what you want. You want your program, unless you have a bunch of random number generators with different seeds, you sure hope that they return the same thing every time. All right, so this is actually, there's actually stuff, there's output from this example on the slides if you want to look at the slides. I don't know, I can just bring those up. I pretty much said all of this stuff. Again, if you run this again, you're going to get different results. So the next thing, I just want to show you one of the options. Okay, you can explicitly return your results as either columns or rows. So it's combine equals rbind or combine equals cbind. And this isn't going to work either. But again, I just wanted to show you that option. Oops, I think we need to start our cluster again. So here are our results. Okay. And basically, here's the same thing. Oops. That's the row version. Did I? Yeah, it looks like I did. I guess we're not going to run that. Sorry. I could reload this, but that's all right. I mean, basically, we'll see this. Instead of vertical, things are horizontal, and we'll see that. Anyway. All right, so this is where things are going to start to get interesting. Again, this does not work properly, but we're going to start to see why. Okay. And what we're going to do is we're actually adding to the output the process ID of everything that's running. Okay. So here we're getting the process ID, and then we use the C function. I guess that's what it's called. Would that be cat? Yeah, cat name. All right, let's clear this. Oh, okay. And if you're looking at the slides, you'll see that it actually says this is going to return exactly the same thing unless you put set do print to true. Just get rid of that and run it. All right. So here, again, we have a bunch of numbers. These are the values that were set. But here's the process ID. Okay, now I'm going to go back to the slides. This has this a couple times. Oh, come on. being very picky. Ah, here it is. This is the one I wanted. All right, so we've talked about we've seen this already. So we're returning the values, get a different sum. Okay, so should be plain. So this column is the process ID, and what we see, and it's actually sorted by process ID also. What we see is that we have this loop, and different processes are acting on different elements in that vector. And things are not necessarily always done in the same order. And in general, math is no longer commutative. Here's the same thing again. This time we got 85 when we summed everything up. But we have a different set of process IDs, and they are actually, this is actually the element here of that vector on which it is operating. And remember, this is trying to do a sum over all these values. And you're getting partial sums, and the partial sums, you can't just add them up. You got basically it's stepping on itself. So here's the same thing, but the only difference here is that we ran this twice, but we didn't do a stop, the stop and restart. So we have the same set of processes, but even with the same set of processes, you're not guaranteed to get the exact same results. Okay, so enough of this. Let's actually start to look at something that's going to start to actually work. Okay, so what we've done is that we have created a matrix, okay? And we've actually filled it with using the R norm function. And we have set the seed to be one of the values, okay, from the for loop. Okay, so this will go from this will actually go from 1 to NT, and each time we call this random number generator, it is actually called with a specific seed, okay, which is determined from this value. And what you'll see is that we could run this however many times we want, and you'll actually get the same result every time. Okay, so what are we seeing that's a little different? Okay, what we're seeing is that we have some consistency from one run of this code to the next. And our calculations are actually taking into account that they're actually being run in parallel. All right. So let's look at, go back to RStudio, and we'll go down to number 9. And let's look at what we're actually going to be doing here. Okay. So in this for loop, okay, what's different? This is actually, again, going to return, it's going to work in the sense that it's going to return the same values every time that you're doing the calculation. So what is different? We have whatever is in the loop is actually dependent on the indice. So you're actually getting a different value for every element of this loop that you're creating. And there's no what's called loop level dependency. Nothing on this side is dependent on anything that's on the other side of the equal sign. Okay? Because that's what was screwing us up in those previous examples. We took a value left side and tried to use that to assign something to the right side. Well, but another process would screw with that value that's on the right side, and you just continually get mixed up and you have no guarantee of what you're going to get. Here we don't do that, okay? This is completely deterministic, okay? You could run this 1,000 times, you could run it on one processor, you could run it on 1,000 processors. You will get the same answer because there is no dependency left to right. Okay. So the other thing that we note, okay, is that we actually were coming in with a value of a sum, okay, and it actually got overwritten. In this case, again, we're not overriding our values for the intermediate values. Down here, we're doing basically the same thing. Again, the only difference is that in one case, we're doing it here, we're coming in with a sum is set as a scalar. Here, we're coming in with a sum set as a vector. The point is, it doesn't matter. It's completely ignored in this context because it's actually on this side. We don't use it. I mean, if we had b sum and then a sum on this side, that would work. But, okay. Same thing. I'm kind of beating this to death, but basically, whatever you're coming in with on a sum here has absolutely no effect because it gets overwritten. Key is here we've actually taken this. This is kind of a cool one. Okay, let's see, main cluster. Yeah. Yeah, let's see, let's go on. Let's see, did I stop it? Yeah. So this is still part of number 10. So we actually have an example that works. We have oh shoot, run. We're getting the same values each time, and again, we have the same set of process IDs. They don't necessarily run or do the same loop iteration each run, but they will actually return the same results. Let's stop this. All right, we're going to skip that one and go down to 12 because they're basically the same thing. And let's actually look at this one again. Okay. Oops. All right, so in this case, what we're actually going to do we're working on a matrix. We define a matrix. Okay. And then we actually use that, the mean from that. We define a matrix, put some values in the matrix, and then use that with the R norm function to generate random numbers. And then these are printed. Go back to our studio. And again, we will get the same results every time we run this. I would encourage you to actually go through these, and we really didn't have time to really go through them in a whole lot of detail, but go through these examples and see a lot of those that I had there flat out didn't work right. Understand why they didn't work right, and then go through the ones that did work and understand why they did work. Anyway, so we don't have a whole lot of time, and I really, really want to get to the other topic. All right, so we'll actually quit this for now. Back to our slides. Yeah, I should mention this. I briefly mentioned this earlier. You guys remember that spawn application, or the spawn thing that I said probably or didn't, turns out it doesn't work on the machine here locally. You can actually use that with this parallel package and have multi-level parallelism. To get that to work properly, really what you want to be able to do is you actually want to be able to control where the tasks are spawned. And so this is actually a little routine. I actually wrote this for a professor on campus because what he was seeing when he was using the spawn, or actually just the parallel package, it was actually getting multiple instances of R running on the same core. So the routine shown here, you can actually force instances of R to a particular core. And here is a matrix inversion example. Note that we have the for each. So we're going to do some number of matrix inversions in T. They're all independent. We define our matrix here, and then we call the solve routine. Again, this is a routine that works fairly well in R if the R was built with support for Intel's MKL library. If it is not, it's slow. There's like a factor of 10 difference between LAPAC and MKL. So if you want information on that, send me an email and I can actually show you some hard numbers on that. So what's happening here is we're creating a matrix and solving it. All right, some number of them, each one of those is done in parallel. This is the routine that I wrote, or this is how you would call the routine that I wrote that actually maps them to individual cores. Okay, and then you've seen this already. This is the spawn application. So what we're doing here is we're actually using spawn to grab multiple nodes. Okay, we grab 2 nodes with MPI. Then on each one of those nodes, we actually run the matrix inversion example with some number of inversions. So what is reported is the number of matrix inversions, and we're running on 2 nodes, so each one of these numbers is duplicated. And then this is the runtime for those matrix inversions. It stays constant, or fairly constant, because as we are adding more inversions, we're just going to different cores. So until we fill out the machine, we actually basically are growing the amount of work as we add a number of matrix inversions. Okay, so skip that. We've seen that, we've seen that. All right, I got 15 minutes to tell you everything there is to know about earthquakes. So there's a database of earthquakes. There's actually many, but the one we're going to talk about today, earthquakes in Southern California from 1981 to 2018. There's 600,000 plus in this database, 94 megabytes. I actually learned something from doing this analysis. I was stunned to find out that earthquakes are more likely to occur at 11 and 1 o'clock. There's actually a slight increase at 11, dip at noon, another slight increase at 1 o'clock. I mean, it's like less than 1%, but it is, you know, over this many years, I think that's probably significant. All right, so this is where the data came from. Again, and this is classic stuff that you would do in R. It is just a huge table, 600,000 lines long. So our goal is to create an earthquake hazard map for Southern California. We're summing, in some sense, earthquakes. We get the maximum and the sum of the earthquakes. We're actually looking at summing the acceleration or maximum velocity. They actually are very closely related, so it doesn't really matter which one we're doing. So our earthquake intensity at a particular point is a function of the distance and a function of the actual magnitude of the earthquake. Oh, timer routine. This timer routine I wrote. I have this routine. It's really cool. The way this works, the first time you call it, it returns 0, 0. Next time you call it, delta t. Next time you call it, small delta t and big delta t, and this becomes cumulative over time. So it's a really cool routine for timing individual sections of code, and you can actually reset it. So this is in with all the other stuff. So here's our functions for calculating our intensity. It is a function of the actual magnitude of the earthquake. It is a function, attenuation as a function of distance. And you take those two together, calculate the distance based on latitude and longitude and depth. If magnitude is greater than 0, because some of these earthquakes in this list, they're just sort of like, we don't know what it is, so we just assign a negative value. So you just throw those out. So if it's greater than 0, then you actually add it to your list. And if not, you don't. And the disclaimer here, this is basically bogus. As I said, I've done earthquake simulations. These have the sort of the same, the kind of the right shape, but earthquake simulations are extremely complex. There's no way that you could actually do this for real in something this simple. All right, so start this up. We have two versions of this, actually more than two, but we have an MPI version and the parallel 4 version. MPI, we do the ComWorld, ComRank, do the initialization. Here, we just load the libraries. These are actually routines that were used to actually draw the maps. They are actually not used here, but it was just part of my original code, so they're still in there. All right, so we read the data. Again, it is a table, 600,000 lines long. These are the headers. And I'm going to go over. All right, so this getData.py, the parallel 4 version takes the whole thing as a individual file. The MPI version actually we break the data up into sets, and this getData.py actually did that automatically when you downloaded it. If you run that again, you can break it up into different sizes. By default, it breaks it up into four different sets of hopefully equal numbers of lines. So this is a loop in MPI. What we're doing, we're looping over. We start out. Oops. We start out outer loop, longitude, latitude, inner loop. We loop over our tables, our table of earthquakes. This turned out to be a bad idea, as you will see here shortly. This is our loop for the parallel 4. Again, here we're actually looping over our longitude values. Again, turned out to be a bad idea. All right, so then this is basically just saving the data when we get out of those loops, either the MPI loop or the parallel 4 loops. And what we're saving is a maximum in our data structure, and we also save that as a CVS file. This is saving the data in MPI version. And there's actually, okay. So this is another version of the MPI program where instead of looping over longitude and latitude as the outer loops, we actually loop over the rows. And you'll see here shortly, this is the way it should be done. A whole lot faster. There's actually something missing here. I need to, there's something that did not get on those slides that I need to show you. And it's these two lines right here. So each one of the MPI tasks calculates their for their set of earthquakes. Okay. And then what we do is we actually use the MPI calls reduce to do two things. The first case, we actually sum the values. Okay, so we're actually taking the individual sums of the earthquakes from each individual MPI task. And then the second line there, we're actually doing a maximum. So as I said, we want the sum of all the earthquakes and the maximum of all the earthquakes. So after those two calls, the root process has the maximum and the sum of all the earthquakes. and then we just print that out with the saving the file. I've actually shown you that already. And then the other thing is, this is just a sanity check. We actually print out the 4 corners of our grid just to make sure things actually worked. So back to this. All right, so small test. This is my test case, ran on a 6x8 grid. Our latitude and longitude limits, 35 to 32, 6 values, minus 121 to 115, 8 values. The full size grid was 101 by 176, so 555 times bigger. And this is our data set, 634,000 earthquakes. And this is the parallel 4 version. Ran in 343 seconds. The MPI version was a little bit faster, 273 seconds. Okay, whoops. So the 200, and then this is the second version of the MPI, where I put the earthquakes in the outer loop. It ran considerably faster in roughly 29 seconds. So, well, no comment. So this is our the versions of the program, and 343, 273, 29, and no comment. I will say that for the no comment run, most of that time was actually in reading in the data. Calculation didn't actually take that long. So for the full version, ran it on 24 cores of Summit, which is similar to your machine here. Took 1,093 seconds. And the answer is, or really, it's not an answer. The question is, would you like to buy my house in San Diego? No takers? It's a nice house. But in reality, we just discovered the San Andreas Fault. So exercise for the students. So take that, that parallel 4 version and move the earthquakes to the outer loop. And what you probably want to do, the same thing that we did for the MPI version, and instead of actually putting or sending into the loop the list of earthquakes, what you probably want to do is send into the loop a list of files. And then inside of that, then read in the files and do the calculation. So you don't even have to send the data in to the parallel 4. You send in the name of the file. It's going to be a whole lot faster. And I think the rest of this stuff is the stuff that was not particularly R, and you can look at that. Anyway, I'm done.
I think we have time for some general Q&A for Andy Anderson here. If you guys have any questions? If not, on the course website, you guys can end up through Wireline on. There are examples of how to do the MPI stuff on Peacock. So Simon can do that for us. So you can take those.
So this is actually the first time I've done this. So sorry if it was a little rough, but guess that's it. How do I turn this off?
Okay. I'll let you guys coming up from Colorado help us out. All right, Zoom folks, we are going to sign off here unless there's any questions, but that workshop Google Doc is still available. So if any questions come up that you have, write them in there and we can check them out later. And then obviously we'll email you with those questions.